This is #1 champion sound. Yeah, Estelle, we about to get down. Who the hottest in the world right now? Just touched down in London town. Bet they give me a pound. Tell them put the money in my hand right now. Got a promoter, we need more seats. We just sold out all the floor seats.
Take me on a trip, I'd like to go someday. Take me to New York, I'd love to see LA. I really want to come pick you with you. You'll be my American boy. He said, hey sister, it's really, really nice to meet ya. I just met this 5'7" guy who's just my type. Like the way he's speaking, his confidence is peaking. Don't like his baggy jeans, but I'ma like what's underneath it. And no, I ain't been to MIA. I heard the Cali never rains and New York's wide awake. First let's see the West End, I'll show you to my bedroom. I'm liking this American boy, American boy. Take me on a trip, I'd like to go someday. Take me to New York, I'd love to see LA. I really want to come pick you with you. You'll be my American boy, American boy. La, 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 la. Will you be my American boy, American boy?
Yo, yo, yo. How you guys doing? Alright, we're sorry for the late stream, but in 1 minute, we're going to be going to the Division 1, which is going to be Bridgeway. I hope you guys are ready. Alright? Alright, wish you the luck.
Recording in progress.
And I also have experience in project management infrastructure for more than 40 years. Thank you.
My name is Emre Erkmen. I'm an assistant professor at Concordia University. I have a PhD from University of Ottawa. My background is in structures and mostly on computational mechanics. Thank you, guys.
All right. For each of you, would you like to just say your program and what year you're in? Just
sure.
Before you start.
I guess I'll go first. I'm in my 3rd year of biomedical and mechanical engineering right now.
Nice.
I'm sorry. Oh no, sorry.
Oh, and I'm in my 4th year of civil engineering. I'm Annika.
I'm Devin, and I'm in my 6th year of mechanical.
I'm Shannon. I'm in my 3rd year of civil engineering.
I'm Melissa, and I'm in my 2nd year of environmental engineering.
And I'm Melissa, and I'm in my 3rd year of architectural engineering.
All right. So whenever you're ready, one of you can share your screen. You can time it. Well, it's 7 minutes. You could time it however way you want. I can give hand signals like 5 minutes left, 2 minutes left, 1 minute, 30 seconds. I don't know if that's helpful or distracting. Sure. Yes? Okay.
Might as well.
Okay. And yeah, whenever you're ready.
Okay, cool. So as you all know, we are Bridgeway. We hope you are hungry and ready to eat a sub. So we did already kind of meet the team, but here we are in our beautiful filters that we made. Quickly, I guess, once again, I'm Brooke. I'm one of the co-captains.
I'm Devin. I'm in 6th year mechanical.
I'm Elise. I'm in 3rd year architectural.
I'm Melissa. I'm in second year in Biro.
I'm Annika, and I'm in my fourth year of civil, and I'm Brooke's co-captain.
And I'm Shannon. I'm in my third year of civil engineering.
So this is a side elevation of our bridge that we produced in AutoCAD. We also drew a top view and front view of our bridge as well. Our drawings show the important dimensions, including our overall span of 600 meters, our water clearance height of 7.4 meters, our deck width of 18 meters, which includes 2 traffic lanes and 2 lanes for pedestrians and biking. We also assume that there are ramps on either side of our bridge that are not modeled for traffic to enter and exit the bridge.
This is the 3D model that we developed for our bridge design. And initially we did run into some trouble developing this model just through issues with Civil 3D, but we are proud of the result that we came up with. And although it doesn't resemble the classic 3D model of a bridge, it does show all the key characteristics. So we are happy with our results. And the structural members of our bridge will fail in one of 2 ways. When there's an increased compressive load acting on the bridge from the live load and the dead load, so the self-weight of the bridge, the weight of the traffic, pedestrians, etc., it will cause the vertical members of the bridge to fail by buckling. But when there is an extreme compressive load acting on the bridge, this will also cause the horizontal members to become overloaded and fail by snapping. The truss type that we chose for our bridge design was the Parker truss. And the Parker truss contains an upper chord in the shape of a polygon. And this upper chord is composed of very straight sections that when combined appear to form a curve. The Parker truss, it's a variation of the Pratt truss, but it uses less material, so this makes it both more cost effective and sustainable.
So when we did our load analysis, we decided to consider a uniform weight distribution just to simplify our calculations a little bit, with the maximum amount of semi-trucks occupying the bridge sort of as a worst case scenario type of calculation. Then we used the relationship between weight and area to find the upwards and downwards directional force values. Doing that required, sorry, the different densities of our materials to be considered. So we made sure to choose those carefully to make the bridge as strong as possible. After those calculations were completed, we did find that the downwards forces were about 2.6 times larger than the upwards forces, which unfortunately means that the bridge would fail under these given conditions. Looking back at it, we did forget to consider the reactionary forces caused by the ground itself, which would have had a significant impact towards the upwards forces, helping it to stand. So that's something that we would have changed if we got to do this again.
All right, and as Shannon already mentioned, this is was selected to be a Parker truss type bridge that would span 600 meters across the Ottawa River. And a little bit about the dimensions. So we were required to have a clearance of 6.7 meters from the water level to the underside of the bridge in order for boats to be able to pass underneath. So with 600 meters as our given length, we decided to subdivide the bridge into 3 sections. So have a primary column about 200 meters into the bridge and then 200 meters in from there. So at those points in the Ottawa River, the average depth of the water is about 38 feet, which is approximately 11.6 meters. So as a team, we decided to round up to 19 meters for an overall column height from the ground in the water to the underside of the bridge, which would give an overall clearance of about 7.4 from the water level to the base of the bridge, providing a little bit of extra leeway in terms of size of ships that could pass underneath. Now, also a little bit about the width. It's about 18 meters. So 2 traffic lanes and 2 pedestrian slash cycling lanes on either side of the bridge.
And the bridge is made up of mostly steel in order to make it more affordable, sustainable, and weather resistant. Building a bridge here will come with a couple negative environmental impacts, from just general construction to disrupting the marine life in the river. However, there are more positives with reducing gas consumption from the ferry. It promotes biking and walking. Keeping the bridge only 2 lanes limits the destruction of land and surrounding trees. And easier access to the park will bring in more visitors and financial support to maintain and protect the wildlife in their habitat.
So the free flow speed was determined based on various adjustment factors that were influenced by the design of the bridge. So such as lane width, lateral clearance, medium type, and access points. So after finding about a free flow speed of 87 kilometers per hour, the heavy vehicles factor had to be calculated before we found the peak capacity of the roadway. So based on the information that was given about truck percentages, we found the factor to be 0.94, and that determined a peak capacity of 2,571 passenger cars per hour per direction. And these values were determined a density of roughly 30 passenger cars per kilometer per hour, which was cross-referenced with the level of service criteria to find a level of E for the roadway, which it's not great, but since the roadway is not heavily used, since it's in a very rural area, the design should be sufficient enough. And we would like to open up the floor for any questions.
All right, thank you very much for that wonderful presentation. Yes, questions from the judges. You guys have 6 minutes.
Okay, so I think I will start with the first question is why you selected the Pratt test trusses pattern, and do you think that's all the members in that will have either the vertical in compression and the diagonal in tension?
Not all the members will fail by either the vertical or the horizontal failing. The diagonal members, they're acting as bracing for the truss bridge to help support it and avoid failure.
Yeah, but in your report you said the vertical members will be in compression and the diagonal member will be in tension. What about the horizontal, and is there any vertical member will be in tension as well?
Well, the bottom chord of the truss bridge, the horizontal members will be in tension, and the top chord, the horizontal members will be in compression.
Okay, so the statement that only the vertical will be in compression is not accurate. Whatever you said that just now is correct, 100% correct. What I'm saying is the statement in the report cannot be, it's contradicting with what you said. What you just said is correct. What is written is not correct. Okay, so that's one. Secondly is, if you feel the failure is a buckling, can you avoid that in design? I think someone is frozen. The screen is frozen for Shannon. Who's gonna answer this question?
It looks like it.
Yeah. I think.
I feel like maybe for the future, for the next year to improve the bridge, it would probably be the area, definitely the area of interest. Just different ways to improve it could possibly be, just trying to think off the top of my head. Like additional reinforcements potentially, maybe not having cords, but more sturdier members to take off some of the load.
Okay, fair enough. And why you select steel against concrete?
So we actually chose concrete for the beams, but steel for the deck and the wires. Excuse me. And we chose that based off of a little bit of research that we did that said that the concrete beams that we chose wouldn't crack in the winter and were the best, like cost efficient wise, whereas the steel for the deck added some strength and again was like a little more cost efficient, as well as we found somewhere that said that steel is one of the more sustainable materials and that it can be like recycled better and is a little more cost efficient. So that's where we chose our materials from.
Okay, then maybe another question. I will leave it to Dr. Emre, and after that, maybe I will come with one question. Thank you.
And just continuation of Dr. Andy's questions. What about the columns, the piers? Is it
Yeah, so the
concrete?
like columns are all made out of that same concrete. And it was like a crack resistant, quick dry concrete. I can't remember the name of it right now. And then the wires were made out of steel again.
And you mentioned that your system is a bit different comparison to the classical one. What is the main difference in your 3D? When you were showing that, you mentioned that.
Yeah, so our 3D model is because we were having some issues with Civil 3D, we were sort of running out of time. Although it does contain a lot of those characteristics that we were hoping to show, rather than more of like a solid 3D model, it kind of looks more like a mesh. So that's where it would differ in that way.
Okay, so did you consider any lateral supports between the two frames, or is it two frames on the side, right?
Yes.
And did you consider the how you tie those two frames to each
Yeah,
other?
so up at the top, we connected those across, and then I believe we also did sort of like an X shape connecting those as well, just to add more stability.
Okay. Yeah, I'll stop here and leave Dr. Ali to continue.
Thank you. So one more question is, have you considered what type of support in both end of the between the spans? So you have like about 3 spans, is that correct? So what are the supports in both end of the span? What type of support? Yes.
Originally, what the at the start of the design process, we had intended to have it arch over, and so gradually slope up at about an angle of 2.1 degrees over 200 meters to like the first column, and kind of arc just over the water, just at a low level, about 7.4 meters at like the maximum. So flatten out between the two columns. However, as the design went on, for time's sake, we decided to do the flat just deck, and then support it with it would be most likely the similar columns
soon
at
we'll be moving on
either
to
end, and then have
the
a
next
ramp that would
presentation,
probably slope up a little bit more,
which is going to be the
I guess steep,
trust nobody.
over a shorter distance at either end.
Wish us luck.
But the question is,
I hope you enjoyed the first presentation.
Sorry. Is it like you consider fixed?
Let's go.
For all?
All right.
To identify any geographic concerns and constraints.
And
beyond that, we were given constraints in the challenge guide and eventually came up with our design. Next slide. So some of the constraints we followed were related to location, software, deck design, and environmental issues. So in terms of location, we were able to abide to existing structures and the capacity of roadways in the town already. The deck design had to do with span length, entry and exit of the bridge, and lateral distances that must be achieved. The softwares were limited to AutoCAD and Civil 3D. And finally, the environment must be respected, as natural life surrounding the site must not be disturbed, and the process must keep sustainability in mind.
Before hopping on AutoCAD, we collectively decided a few key measurements. As mentioned, there was a constraint on the height of the bridge. The height of the bridge itself is 6.7 meters above the water, allowing for clearance of boat traffic. There not be any major supports in the middle of the span of the bridge, ensuring that the boat traffic is not stalled. Next, the distance between the two docks was 500 meters, but we decided to add an extra 20 meters on the side of the thurso, as would ensure the ramp begins before the dock. This decision was primarily made due to flooding concerns present in the area. By pushing the ramp back 20 meters, it allows for support to be on land instead of in the water to ensure no water is displaced towards the residential side. There will be single lines going in each direction, each with a width of 3.75 meters, as that is sufficient to accommodate both regular vehicles and heavy ones as well.
So on this slide, we have our final design. The left side of the drawing is the entrance ramp from Clarence Island, and the right side will be the entrance ramp for Thurso. There's a discrepancy in the size of the support, since one side will be fully submerged and the other will be on land. We used arches spanning from either side of the bridge towards the middle, and to increase the aesthetics of the bridge itself, we included angled members going to the top of each arch. To be economical in our design, we didn't add anything super funky, so it's quite simple.
As we mentioned before, one support is larger than the other. We have the drawings here. The left side shows the support on the thurso side and the right side is on the opposite side.
To justify our specific design, we wanted to talk you through a few different parameters that we used. So the first one being the span height. Like the rest of my team mentioned, we had a specific constraint. So we decided to have a span height of 6.7 meters. Next, we want to talk about the length of the bridge. So we did surpass the 500 meters between the two docks, but this was entirely due to flooding. So we wanted to push back the entrance ramp on the residential side so we wouldn't have to worry about flooding as much as we would if we displaced water. Next, we want to talk about our incline and decline ramps. So we decided to have an angle of 15 degrees, which correlated to about a 25-meter long ramp. This was both because we felt safe doing this and we didn't want to create anything insanely steep, which would kind of lead to flooding concerns again and would cause problems in slippery weather and in the months of snowfall. Furthermore, to be kind to the natural habitats in the surrounding areas, we plan to use modular construction. So this will allow for the bridge to be built in a remote factory away from the small town and the ferry lane. So it can be transported and put together on site. This will minimize job site waste and reduce the negative impacts a construction site would have on the natural habitats. Also, we recognize that the bridge is built to connect a small town to a natural island. Therefore, we will include a shared pedestrian and bicycle lane, which will be divided by a concrete railing for both the safety of the drivers and the pedestrians. For the load analysis, we presented you a worst case scenario in our report where we provided a calculation that covered bumper to bumper traffic in both lanes represented by a large uniform distributed load. So we took another approach as well. And what we did was we used our analysis flow rate, which was 45 PCU per hour, and multiplied it by the weight per PCU. And we found that each support reaction would be going through a reaction of about 525 newtons per side per minute, which is equivalent to about 54 kilograms, meaning it is a very small load, making a third support redundant. And we did not do any internal force calculations because we thought that the external supports seemed fine the way they were, and we didn't want to create unnecessary cost and environmental impact.
So since we already discussed sustainability in the previous slides, I'll move on to our design. So we found our free flow speed to be at 90 kilometers an hour with a level of service at level A. So this means we were able to create a speed limit of 100 kilometers an hour on the span of the bridge. So this creates an efficient connection between the two pieces of land. The flow rate used was found from Google Traffic Service as linked in our challenge guide. So we had to use that number to find the PCU per hour and then adjusted it to the 7% heavy vehicle load. And with that, we ended up with a final adjusted flow rate of 45 PCU per hour. We discussed the topography in the area as well as used the different supports to accommodate for the area.
Overall, we really enjoyed working on this project, and we wanted to thank you for your time and for listening.
Great. Thank you guys so much. You ended a minute early, so we are going to have an extra minute for questions and answers. So you have now 8 minutes for questions and answers from the judges, and your time starts now. You can stop your screen share.
Oh.
Anne,
okay, I'll go first. You mentioned a 15% slope for the approach. Can you explain, like you kind of justified why, but where did you confirm that 15% would be an appropriate slope?
So we did a lot of research and we couldn't exactly come across anything that would tell us specifically as to what would be like an acceptable slope versus what wouldn't be. So we kind of got together and talked about our collective experiences of driving on different kinds of roads in different kinds of areas. And we felt that 15 degrees would be relatively fair just because we wanted to keep our driving area safe. And we also wanted to not disturb any traffic in the water. So as a group, we collectively agreed that 15 degrees was a pretty fair number.
Okay. You put one of your abutments in the water, which is fine. But did you consider in your design the impact of loads that are found in the water. So the pressure of the water as it flows by, ice, when it breaks up, all of these things. Were those factors considered?
Like, I don't believe they were considered. It was more so a consideration of being respectful to the natural land that we were connecting. So we felt as if though it would be in our best interest to use a support that would be deeper. It would be a deeper connection to our bridge through the water bank. So that's why we ultimately decided on using a support that was fully submerged. We didn't exactly consider any like hydrostatic pressures or whatnot.
And one last question I have is regarding your use of permeable concrete, I believe, for the deck. Can you explain to me why you went with permeable concrete? And
Yeah, so in the challenge guide, they discussed a lot of flooding concerns, right? So we've actually, in our second year, we talked a lot about different forms of concrete, and we found that permeable concrete tended to be a reliable solution in some specific communities that experienced heavy rainfall and runoff water. So we kind of applied that knowledge that we gained in one of our initial structural classes and brought it here, just because we thought it would be a pretty good solution to kind of combat any flooding on the main span of the bridge.
I was also gonna say, like, concrete is just like very versatile. Like, even though it's really bad for the environment, at least permeable concrete was a type of solution that they were able to come up with, concrete that kind of was able to work with the environment in a way, even though concrete naturally isn't very workable with natural environment.
okay. Over to Alex or Talish.
Hey guys, so beautiful presentation. You guys did a great job at explaining and justifying your designs. One of my main questions is you guys might have went over it a little quick, but the main points of failure of the actual bridge. Whenever you guys were going through with your design, did you sort of consider the inserting a pier for the actual design and like countering the points of failure with the potential flooding, or how did you guys sort of take that into account in your final design and justified why you went with the design you guys went with?
I'm sorry, would you mind repeating the pier
Yeah,
part?
for sure. So like you guys have basically a free span bridge, right? And you guys did not design it with a pier in the middle or at any point. And the main reason why you guys didn't do this is due to flooding or potential flooding, so on and so forth. But whenever we are considering the points of failure of a bridge, a big point of failure of any bridge would be the middle part of it, right?
Yep.
So when you guys were designing it, how did you guys justify not putting a pier there versus putting a pier there?
Yeah, so what we've been learning a lot about now is learning to be right with our analysis and also being economical with our kind of the products that we use to build our bridge. So we went in and then used our analysis flow rate to find out how much of a load the bridge would be going through at any given time. And we found that it was completely acceptable to keep just the two supports on the outsides versus making sure that we're not causing like the high bending moments on the inside, which would kind of lead to the cracking inside the middle of the bridge. So we ended up justifying the use of 2 supports versus 3 based off the loading that the bridge would face on any given day, based off the analysis flow rate that we found.
Okay. Oh, sorry. Okay, yeah. And is there to your design, is there any other potential things you guys think you could have considered to sort of counter the increased amount of points of failure in your design? Is there anything else you could have done to sort of reduce the amount of points of failure is my question.
Does anyone else want to take that question? No? Okay. I mean,
Actually,
Okay, go ahead, Monica.
I was going to say that you mentioned the hydrostatic force. I think it would benefit us to look into that more with the one that goes into the water. That's what I was thinking at first.
Yeah, so just like thinking about all the extra forces that we need to consider as support going through whenever it's submerged in water might be a good idea, just because we don't want to get cracking really close to support, right? Just because we feel like it just become counterintuitive at that point, like it's not really doing much for the rest of the span of the bridge. Other than that, we found that like just like intuitively it would crack at the middle. So other than a third support like going through the middle, there wasn't much we really discussed in terms of potential failures.
And what about the double arching cable system you guys chose to go with?
Yeah, so we ended up doing that as we used the arches more so as kind of as aesthetic purposes, right? So we do recognize that there will be additional compressions within the middle of them, right? As the arches are in compression and the cables will be in tension. But again, we just thought that the entire loading system on our bridge did not justify having a major support being submerged in the water.
Thank you, guys.
I'll go next. Nice presentation, first of all, and I'll start with my questions. For your highway on the bridge, my question is, how do you justify not having...
I'm sorry to interrupt, the time is up for the presentations. Move on to the deliberation session. I would ask the contestants to stay here, and I'll move the judges to the judges' room.
All right, well, yeah, he said it for you guys. Now this time is up. Now we need to move on to James Bond License to Glue. I really like that name, to be fair. Okay, that should be the third presentation. So it should be right here. But we really do hope you enjoyed that. All right, now we're moving on. This should be that.
Yeah, it's pretty cool.
It is pretty cool.
Just the 3D,
They're right.
The 3D is lagging a bit.
All right, wish them luck.
I think we can let them in.
Yeah, I'll let them in.
Yeah, Ermin's gonna send them.
Hello guys, you can start presenting whenever you're ready. You'll have 7 minutes to present, and Elsa will make hand gestures when your time is almost up.
Perfect.
Okay, thank
sounds
you.
Good. Can everyone see the presentation?
Yes.
All right, great.
Perfect. So we are James Bond's License to Glue, and this is our Troitsky 2022 presentation. So my name is Natalie Dixon. I am in Mechanical Engineering and Society, year 3 at McMaster, and this is my 3rd time doing Troitsky.
Hi, I'm Lucas Hildebrandt. I'm in Civil Engineering and Society 3, and it's my 3rd time doing Troitsky.
My name is Hamza, and I'm in my 2nd year of Civil Engineering, and this is my 1st time doing Troitsky.
My name is Selena. I'm in 2nd year Civil Engineering Society, and it's my 1st time doing Troitsky.
My name is Nicholas Grislak. I'm in 3rd year of Mechanical Engineering and Management, and it's my 1st year doing Troitsky as well.
Right, so our bridge purpose. So we were tasked to design the bridge that connects between the city of Thurso and Clarence Island, which is on the Ottawa River. Currently, there's a ferry there. However, due to lack of use in winter and just general growing demand, we are designing the bridge to replace that and be a better product. So we designed a simple steel girder with concrete deck bridge and with concrete supports. Our bridge will have 1 lane of vehicle traffic in each direction and then 1 lane of pedestrian traffic in total as well.
So as mentioned before, our bridge will span the Ottawa River to connect Thurso to Clarence Island. We chose to put the bridge where the ferry is currently operating for a couple different reasons. Mainly because the infrastructure there is already in place to include a bridge. So the roads come right up to there and then goes across and continues on the other side. It's also already built up around that space to allow for a structure to be put on top. So we wouldn't have to to damage as much of the surrounding environment. And this won't interfere with any of the residential houses around the area. We do understand that there might be an issue as the ferry would not necessarily be able to operate during the time of construction, but with a little bit of research, we did find that there's a ferry in the next town over. So we think that this wouldn't be too big of an issue, maybe just a little bit of a minor inconvenience.
And for our design, after we measured about the distance between the river area, we made up a bridge that's about 550 meters long, and then we also have a top platform at the bridge that's like about height about 9 meters, and the flat surface is about 100 meters long. This is can allow like boats to go in through under the bridge, and about every 50 meters we also have a pillar, constructing with concrete and steel I-beams that supports the weight of the bridge, and on the surface is a 9.2 meters wide road. We also added a pedestrian road on the left, allowing like bikes and pedestrians to cross the bridge as well. And we also added the concrete shoulders to protect pedestrians and create this distance between the pedestrian and the vehicles. And here's like a top view. We can see the pedestrian line on the left and then the vehicle line on the right, and just the layout.
So this is our civil 3D model. The first thing you might notice is we are missing the concrete supports under the bridge, so it is kind of floating. This was just due to a bit of us struggling using the software and running out of time. So it is just a bit of a long road, but you can see in the one picture, you can see our pedestrian walkway, which could also be used as a bike lane, and the 2 lanes for traffic, as well as the shoulders on either side. That big block you see there would be a fence. Just based on our limited knowledge of the software, we couldn't really make it pretty, but in real life, we would hope that that might be something a little bit more decorative, as it's more for just protecting people as opposed to actual cars.
So some features of our design. So it is trapezoid shaped as shown in the previous image, and it's steel girders with a concrete deck on top. So we've got a slope up to the middle span. So the middle span is our full height at 8 meters from the water level to the bottom to allow boats to easily pass through. We decided to slope it up so that way we could use less material in the supports, as they wouldn't need to be as tall, and just to make it easier for cars to travel. Each support, obviously not shown, however, would be 50 meters, like 50 meters from each other. This is in order to keep a relatively low span on each one and lower the amount of force pushing down.
So the total bridge span comes out to be 550 meters, and it's directly perpendicular to the riverbank, which would be the shortest distance across the river. And we made sure the height is high enough in the center of the bridge, so that even if there is a little bit of flooding, the boats can still pass through safely. And we got these heights by looking at other bridges throughout the river and making sure we have enough distance for the boats. And basically each span on the bridge will consist of 4 girders side by side. So here's a simple load analysis. We calculated this by looking at some of the dead loads and estimating a number for the live loads as well. And as we can see in the bending moment diagram, our highest bending moment would be in the middle of the span, and that would be our most likely to be a failure point.
So just looking at some of the traffic around the bridge area, there's a causeway that leads to Clarence Island. And then in Thurso, it's just like a residential road that leads from the ferry to the actual township with houses lining the banks. So we estimated the speed limits on both of those were around 40 to 50, with the causeway just being a little bit lower just due to the kind of the danger of driving right beside the water. With this in mind, we designed the bridge to have a speed limit around 50 kilometers as well, just to not create a bottleneck in Thurso or on the causeway. And with that in mind, we were able to reduce the lane width to only 3 meters. The right shoulder, we did include a small one just for safety reasons and pulling over. The number of lanes, we only have one lane each way. For the median, we do have it undivided just in case of an emergency, and that part of the bridge needs to be closed off by the police cars can still kind of go around any sort of accident that happened. With this, we believe that it was more than enough. We had a free flow stream of 61.3 kilometers per hour and a base cap of around 1,500 cars per hour or around 750 cars per lane. And again, because it's such a rural area, we believe that this actually like helps in the future for just any building up needs that either townships might have.
Thank you for listening.
Thank you.
Okay, great. Judges, do you guys have any questions for them?
Yeah, so you said your span is 550 meters long. In every 50 meters, you have a set of 3 piers. So 11 set of piers, do you planning on having across the river for this bridge?
Yeah, that's correct.
Did you calculate what the current, sorry. Did you calculate what the current traffic is? Like how many cars at peak right now?
I can answer that one. So we didn't do the at peak just because since it is kind of rural, we were able just to look at the capacities around the town. And it was only about like 5,000 to 10,000 cars, which is pretty low density. We were unable to calculate the actual like peak.
So did you consider the environmental aspect of building 33 piers in the river?
I can take that one as well. So with those piers, they would have to be kind of built in the river. But because it is like only, one lane of traffic each way, the actual size of the bridge is a little bit smaller. So we didn't have to build like full on kind of columns or rows. And it's still built just right where the ferry stuff is, just as Natalie mentioned. So there is a peninsula that kind of extends off of Thurso. So it's already kind of built on the water a little bit. And then there's already the kind of infrastructure in Clarence Island.
But
And sorry.
That's the two ends. I'm talking about the piers going in the river.
Yeah, we were also trying to focus on just making sure it's well supported and simply as possible. It would be not quite as environmentally friendly as like we'd like due to all the concrete, but just to keep it like well supported. That's what we opted for.
Okay.
And did you calculate, or do you know for a fact that, first of all, is the middle span 50 meters? Is that correct?
Of the trapezoid, it's like 100 meters long, and then there's like there's 3 then at that top flat part. So there's like every 50 meters still along there. It's
and is that wide enough for the boats to pass?
Yeah, it was I think 6.7 meters they said in the document. So
that was the height, not the width that they needed.
So we actually did ask about this because in the document it does say lateral, and we were unable to get a clear question on that. So we kind of thought 50 would be more than suggested, but also a safe assumption. So
yeah, just if I add in something too, we did look at the Rideau Canal, just kind of down the river, and most of the locks there that kind of bring boats from Lake Ontario to the Ottawa River are around 50 feet wide, or 45 feet wide rather. So we still have like 2.5 feet on each side. And with the span being high, we can have 50 feet kind of going in one direction in one span and then 50 feet in the other to kind of allow like
sorry, feet traffic. Or meters?
Meters, sorry. That's my,
okay.
that's my mistake, yeah.
I don't think I have any more questions.
Okay, perfect. Judges, I'll take you to the judging room to continue.
Okay, this should conclude James Bond license to glue. So right now we're going to the iris. Let's move on to that right now. Also wait for them to populate it slowly. We hope you guys have really enjoyed that one though. And we hope you guys are enjoying your stay so far. All right, let's go on right now. All right, let's wait for them for a bit.
Oh, Yusuf is with us. He's in charge of streaming the presentations. Yusuf, are you gonna stream it?
Currently streaming it actually. Hi.
Oh.
Yeah,
Hello.
you're looking at around like 20, 30 people right now? Or 30 people are looking at you right now.
Wow. All right. Well, thank you.
Doesn't add stress at all. It's okay. You'll be fine.
Good morning.
Good morning.
Good
Hello,
morning.
Iris.
Hello,
everybody. Hi, guys.
I love your backgrounds.
Thank you so much. Thank you.
Okay, that's everyone?
Yep. Could we start sharing screen maybe?
Yeah. First, we'll allow our judges to introduce themselves.
Right.
Oh, so I started myself. My name is Sabah Ali. I have a PhD in structural fire from Carleton. I teach at Carleton and Algonquin Queen, and I have project management experience for about 40 years in infrastructures. Thank you.
My name is Emre Erkman. I'm an assistant professor at Concordia University. My background is in structural engineering and also computational mechanics. I did my PhD at University of Ottawa. Thank you.
All right. You guys want to introduce your programs and years, or are you going to do that in your presentation?
We'll do that in our presentation.
Perfect. All right. Well, whenever you're ready, we're excited to hear it.
Okay. Greetings, honorable judges, guests. My name is Risafa, and my team.
Hi, my name. Hi, my name is Iva.
And my name is Sharon Preet.
I'm Benin.
And again, I'm Sahib.
And we are civil engineering students from the University of Toronto, here as Team Iris. So in the following presentation, we will outline our bridge design proposal to effectively replace the currently incompetent ferry system, facilitating vehicle and pedestrian passage between Thurso and Clarence Island, given we know that the existing ferry system does not sufficiently meet increased consumer demand. Accordingly, here are our main design objectives. That is to firstly, replace the existing ferry line with a competent solution. Secondly, provide a viable and safe connection between Thurso and Clarence Island, which we will visually articulate through our AutoCAD and Civil 3D models. And lastly, to perform analyses to justify the effectiveness of the solution, namely load, traffic, and environmental impact analyses. As you can see from the image, we have chosen to locate our bridge immediately along the existing ferry line, such that the nearby provincial park and the surrounding environment is ideally undisturbed. With that, I'd like my teammate Sahib to take over and introduce our design.
On this slide, we can see the top view and the front view of the bridge. The total deck length is about 585 meters. And since the beam bridges work more efficiently if they're within 76 meters of span length, we chose a span length of 73.125 meters. This gave us 7 separate pillars. We have a separate drawing for the side details of pillars, which is on the next slide. And we wanted to highlight how we accounted for the difference in heights of the water depth by making the pillars in center more deeper. The other thing to note is that we added additional 8 meters to every pillar in order to account for the heights of the boats that will be passing under the bridge. The additional height will also protect the bridge from flooding events. Moving on to the next slide, we can see the design from the side. We chose to keep 2 lanes for each direction and slightly raise the sidewalk for pedestrian access to the bridge. Concrete barriers have been incorporated on both sides, and the total width of the bridge is about 22.8 meters. All of these measurements that I discussed were derived through thorough traffic analysis. Our objective was to not reduce the base free flow speed at all, and we did succeed in 2 out of 3 cases. We kept the width of each lane about 3.7 meters, which helped in keeping the factor of lane width at 0. The inclusion of concrete barriers and the lane and the medians made the right shoulder clearance about 2 meters, and even the factor in table 2 stayed at 0. One thing we couldn't practically impose was more than 2 lanes per direction. This did reduce the speed by about 7.3 kilometers per hour, but Thurso is a small city. So even if we keep 4 lanes per side, we thought that it was not going to aid the traffic flow. Now I'll pass on to Sharanpreet.
Okay, the Civil 3D model of our beam bridge shows the key features we incorporated to best fit the problem statement. To justify these dimensions and explore what influenced our design, we have done extensive research. Before constructing the drawings of our models, the team spent much time researching and analyzing the problem statement. We researched different types of bridges and ended up choosing to design a beam bridge because it was affordable, could be built quickly, and could easily organize ferry traffic. When looking at the river where the design was being built, we decided that a bridge with a short span of approximately 73 meters would be most affordable for a shallow river. Comparing that to the desired location of the bridge, we decided on 7 supports equally spaced from each other. Also, we varied the heights of the supports depending on the water depth, paying close attention to the height required for ferry traffic. Another key design feature was the desired free flow speed. We chose a level of service of D to make the freeway safer while ensuring that the speed was not reduced by a huge amount. There was similar reasoning and justification for many of the other measurements. Now on to Izza.
To determine the weak points of the bridge and the potential points of failure, our team conducted a load analysis. So first we took a point load and we moved it across the bridge, and we used that to find our shear and moment diagram. And then after that, we used data from the average traffic load, and we used that as live load to estimate our max shear and max moment. And through our findings, we found that the most vulnerable point of the bridge was in the middle. And this is useful for like in the future, if we want to add any reinforcements or do inspections, we know to focus in the middle. And now I'll hand it over to Benin.
As civil engineers, our choices largely impact the environment since we are directly working with it. That being said, we all value sustainability greatly. This core value assisted us in realizing the detrimental effects of ferries on the environment, as they account for roughly 23% of sulfur oxide emissions, 13% of hydrocarbon emissions, and 8% of nitrogen oxide emissions. When it comes to sustainability, there are 3 main priorities. 1 being economical, 2 having minimal impact on the environment, and 3 having a minimal social impact. That being said, our bridge aligns with these values perfectly, while ferries do not, making it a perfect substitution if need be. Since the bridge uses reinforced concrete, it has steel in it, and steel meets 3 priorities because it's economical in the sense that it's lightweight and cost efficient. It is environmental because steel is the most recycled material, even more than plastic, and it has minimal social impact because it can be strengthened and adapted, and that means it can last for future generations, and that means less renovating, which will impact our environment.
So through multiple justifications and reasonings, we can confidently say that the bridge designed by our team is the best replacement for the existing ferry system. We took into consideration the environment we built in, and that's how we decided the size of the bridge and type of the bridge. And we also kept in mind traffic and pedestrian load. And we used the average live load data to determine our potential points of failure. And on top of that, we also factored in the environment. We tried to reduce the materials we used and use sustainable options with the goal of minimizing emissions. And because of this, we believe that our design perfectly fits the situation that we were given. And we're open to any questions now.
Thank you. Team, I'm glad to tell you that your presentation is much better than your report. So a lot of information I get it from presentation that I couldn't get it in the report, or it was not clear in the report. So I'd like to clarify some of these. Actually, the report didn't give us a good first impression, but the presentation is actually the other way around. I like the presentation a lot, and I find a lot of confidence when you're talking about that. So I just want to make sure that I clarify some points. One of them in the report, you said the bridge span cannot be more than 76. In the presentation, you say this is the most optimal. And that's two different contradicting statements. So can you explain why you select the 73 and what you mean by 76 is the optimal?
Yeah, I can take that question. So as you can see on our sources, we had one of the sources tell us that the most optimal span in between the beams is going to be 76.2 in between this, the beams. That was in feet. We just had to convert it into meters, and that was the most optimal support. Like if we went more than that, then the bridge would be weakened by a lot. So we took our bridge, which was 585 meters, and we divided it by a number that would give us something less than 76.2 meters. So that means each beam would be strong enough to support that section of the bridge. So the spacing was 73.125, because when we divided it by 585, that's the most optimal length we could come up with based off of our dimensions.
Okay, so Benin, the question is still stands from why it's 76. And what when you say beam, bridge beam, do you mean that it's a concrete beam or a steel beam?
We wanted to use reinforced concrete, but obviously when we go through financing, the materials can change. So we could also use steel depending on the cost efficiency. But once again, by span, I mean the spacing in between each beam. And our total bridge is 585 meters, and we didn't want to have...
I don't want you to waste a lot of time in that because we don't have... I know what is the span. I'm asking why you think the span between two piers is 76. I can make it 150 just to make the beam more stronger. Deeper, give more reinforcing in it. Why 76?
Yeah, that's what I was, when we were researching, that was a number that we found in our sources. It was 215 feet, and that's why we converted it to meters.
Perfect, thank you. So that's my first question, you clarified. And the second thing is, said the bridge beam, it could be concrete or could be steel, but what you select? What is the one that you selected?
We've selected reinforced concrete.
Reinforced concrete, okay.
Yeah.
So you know that if you select a reinforced concrete, you can change the span depending on the design, right? So it is not restricted to 76. I can make it 100, I can make it 150, but depend on that span, I will have my maximum shear, my maximum bending, and then I can decide what are the reinforcing in there. So that 76 is actually misleading. Okay, the other thing is why you select 2 lanes?
I guess I can take that. I talked a little bit about it. One of the reasons for that is that currently the only traffic that flows between Torres and Clarence Island is the one that goes through ferry. And for our design, because the bridge is just about half a kilometer long, it didn't make too much sense to include more than 2 lanes, because even if we keep even if we put like 4 lanes, it's not gonna like allow like a lot of traffic to cross, because the traffic volume is currently is pretty low. And on top of that, adding more number of lanes will require wider supports, and it was going to add to the water forces on the bridge.
Okay, thank you. Finally, I like the environmental section. You covered it very well, and that's good. I liked it actually. Thank you. That's my question. Dr. Emre, if you have a question. Dr. Emre, you are in mute.
Thank you very much. Very nice presentation. Congratulations. In terms of clarifying the system, when you select concrete, decks, did you consider about the construction options, whether that could be, craned, that concrete beams can be installed properly? Could this be any thing that affect your choice as opposed to steel, maybe? Is this something you considered? Let me ask it this way.
So I don't think we considered the construction of the material when we were making the report or the presentation, but that is something we can consider in the future. Whichever one would be more easier and more efficient to install, we would use that material. But right now we thought that reinforced concrete would be a better option.
Okay, is there anything about durability concerns? Again, the perhaps corrosion of the reinforcement, any special caution required in that sense? It's a humid environment.
Rusafa, do you mind answering that, because it's more of like about the loading and failure of the supports?
We did do a structural analysis of that point, and we drew up the influence diagrams to figure out where the maximum shear and maximum moment would be, but I don't think that answers your question. I think that's more about corrosion. So we kind of just used the best material that we could think of, and yeah, I think Sahib, did you have something to say about the flooding?
Yeah, I actually can add up to what Rusafa said. One of the things I think we talked about was that we added additional meters to the pillars in order to not just allow the boats to pass under the bridge in an efficient way, but to also also account for the flooding events that happen, because the pillars will be pretty tall. They're like, as compared to the water depth, they're about additional 8 meters high. So in that event, we think the amount of humidity that is being transferred to the beams and the reinforcement will be reduced.
And maybe one final question: for your points of failure, you identify the midspan between the pillars, I believe.
Yeah.
Just for you to explain, why do you think it's in the midspan?
I think we presumed that it would be in the midspan, and then our calculations proved that it would be. We assume that because it's equidistantly the greatest distance from both pillars. So that's why we assumed that it would have the least support. And evidently so.
Sorry for interrupting. Yeah, just the key thing, I guess, to identify here is, so they're equidistant, and that leads to what in terms of,
like, they're equidistantly the greatest distance from both the supports. So the center is the greatest distance from both the supports. So in that point, I would assume would be the least support obtained from the reaction forces from both the pillars.
Okay, thank you very much.
Thank you.
Do you have time for one more question?
Yes, of course.
No, Gloria.
Yeah, well, it's over if it's very quick, or
no, it won't be quick.
Okay. Yeah, I'm sorry.
Okay.
But thank you so much for coming. Yeah, you guys had a wonderful presentation. The judges, we will go to, once again, we will go to
All right.
judging room 1, and Iris, you guys stay here. We'll come back.
All right, this should conclude the Iris presentation, and now we'll be moving towards Troitsky princesses. That should be in presentation room 2. Let's go.
Main section or the deck of the bridge. So this is if there was cracking or anything along the deck or like just under the deck, then the bridge could collapse or just crack enough to fail it. And then another point is in the arc. So we could have any cracking on the outside or inside. and then that would cause the bridge to fail because the weight would not be distributed properly.
A few assumptions were made when calculating information for the traffic analysis. So we used information from the Alexandria Bridge that crosses the Ottawa River from Ottawa near the Parliament buildings to the Gatineau. And the daily vehicle crossing data gathered there was about 18,000 vehicles a day. And since Ottawa and Gatineau have a greater population than Thurso and Clarence Rockland, we assumed that the volume of vehicles per day crossing this new bridge would be half of the vehicles crossing the Alexandria Bridge. And then with the conversion factor of 0.15 from daily to hourly volume, the number of vehicles crossing this new bridge was assumed to be 1,350 vehicles per hour. So with this information and a calculated heavy vehicle adjustment factor of 0.97, we calculated the flow rate for our bridge would be 1,390.75 passenger cars per hour per lane. We kept the free flow speed at the base speed of 90 kilometers an hour, as the bridge has one lane of traffic in each direction, each with the width of 3.6 meters and a right shoulder lateral clearance of 1.8 meters. And finally, the level of service for the bridge was C.
All right, so for the environmental impacts in the construction process, there's air pollution, groundwater leachate, surface water infiltration, as well as ecosystem disruption. So this bridge will be designed in the attempt to counteract these impacts by implementing a stormwater drainage system, as well as using carbon capture concrete in the general design. So the deck stormwater collection system will divert the water into an input source to the sewer system to limit the stormwater infiltration to the river. And then as well for the carbon capture concrete, we would use Carbon Cure, which is a Canadian company that has dedicated itself to reducing the carbon footprint of construction processes. So this material improves the strength, mixing, and the overall carbon reduction of concrete while reducing the general costs. And thank you for listening and have a magical day.
Great. Thank you so much, Troitsky Princesses. So you ended about a minute early, so we'll have about another minute of questions and answers. So that's your 7 minutes of questions and answers start now, and you can stop sharing your screen.
Alex, you
Yes.
can start.
Yeah, Alex, you can start.
Sorry, I was just finished writing down my points here. Okay. So great team spirit, great presentation. So some questions. Okay, so for the potential points of failure, you guys stated that the middle section and the arches would be the main points of failure. Did you guys consider, or could you guys think of any other potential points of failure within your actual bridge design?
So those were the two main ones we found. And then there could also, we didn't take into account the cables either. So the cables could have been another point of failure. And yeah.
Okay, thank you. Now, relating to the actual arch of the design, do you guys have the span of that arch from where it actually connects to the deck of the bridge?
So like where the deck connects onto the arch?
Exactly.
I believe it was 25 meters up on the arch on either side.
Okay, so the bridge starts, and then 25 meters after, that's where the arch starts, and then the arch goes, and then there's another 25 meters?
Yeah.
Okay. Okay, and my last question is, are there any cables or beams connecting both sides of the arches? I couldn't really see it in the presentation, drawings, but I was just wondering if that was considered within the actual design.
Yeah, so we didn't manage to get them into the CAD model due to time, but yes, there are cables connecting the arch.
And could you guys give me sort of like an idea of how many or how dense they are throughout the actual arch?
Yeah, so they were supposed to be every 10 meters along the deck, so.
Okay, thank you very much. And?
I'll go first.
Akilesh, yeah.
Yeah. Hello, princesses. Good presentation. I liked it. My question though is about level of service. The lowest level of service we can have is A, and the highest level of service is E. You guys must be aware of it. And you guys got a level of service of C, which is 1,390 vehicles per hour per lane, which is quite a lot. And your bridge span is 520. So that's a massive traffic that we're accumulating there if we only have one lane. So how do you justify the choice of going with just one lane in each direction?
That was based off the roads surrounding the bridge. They're all one lane in either direction. That's what we based that off.
You mean the road surrounding the bridge, as in other bridges that are in the parameter, or?
No, just the roads going into the bridge.
All right. And you mentioned, I think Kira mentioned about a right-hand shoulder. Do you guys have a left-hand shoulder too? Just wondering.
We did not have a left-hand shoulder for our bridge.
Any reason for it? For not having one?
It wasn't, I guess we didn't think about it, and it wasn't taken into consideration, I guess.
All right, that answers my question. I'll pass it on to Anne.
Good morning, princesses. So I have a question. How does the deck of your bridge connect to the road?
So that's another thing we didn't get onto the CAD model, but the road will slope upwards on either side. So we'd have to make a slight modification to the road there.
And what, so you're saying slope. So what did you have in mind?
We didn't take that too much into consideration. We just knew that we would have a slope.
You have no idea what slope you would use. Okay. So also, I'm just curious, what loads did you consider in your design? Because I'm especially for live loads, which live loads did you consider? Because I'm assuming from the design that the abutment of the arch will be in the water, because you're 25 meters off. So what loads did you consider in that design of your bridge?
We didn't actually consider any like hydrostatic loads or like loads from ice or anything like that, but we know they do exist.
Okay. Okay, and I think that's basically the questions I had to ask. Second, another thing. Okay, that'll be all. Thank you.
If there are no more questions, we'll move on to deliberation. We will ask the contestant to stay in the presentation rooms for about 6 minutes, followed by feedback session with 5 minutes.
All right, as this wraps up, the next upcoming one should be the Trust the Process. I really like that name. Let's see if they're available right now. This should be in presentation 3. All right, we'll wait a couple of minutes while that's getting ready. But for the time being, how y'all doing? Hope you're having fun so far. Everyone in the chat, I'm seeing you guys, by the way, spam the emotes. That's amazing. Let me see. All right, we should be... let's try joining right now. Let's see where that takes us. All right, there you go.
Two minutes left.
All right. Yeah, sure. There's 2 minutes left.
Wind and breaking force. I know this diagram feels very fake to me.
I'm not sure what they mean by breaking force. The wind part of it makes sense, but and it's actually cool that they have considered wind. But
Loki looks kind of
We'll
cool
see
though.
what they explain.
yeah, exactly.
Because yeah, these slides are a bit fake.
You seem very critical of it.
At least they showed more than one point of failure. That's good.
All right, this gives it... Okay, this gives it 1 more minute. And they should be here at one point.
Hello.
Oh, we got someone.
Hello.
What time are they supposed to start?
They're supposed to start at 11:15.
Okay.
But I guess wait, they have 7 minutes to present.
Okay, this
So
should
you
be
can
the...
start whenever you're ready. I don't know, Isabel, are you ready?
Okay, this is gonna be the trust the process. I like that name though. It's kind of cheesy.
We can give it a minute.
Yeah.
Yeah, hold on, she's not there.
Okay.
We are here. Hi. There you go. Oh my god. I was looking at chat. It's all just emojis and all that. I mean, for a quick minute, I was like, wait, is the chat only on emote only mode? I'm glad. How you doing, Shaving Cream? How you doing, Reggie's? Yeah, living it fully.
I can start sharing my screen.
Enjoying this so far?
Yeah, sure.
Shoutouts. Yo, Super Billy 123, Justin Jen.
Okay, perfect, Isabel.
Yes,
You're
sir.
here, so you guys can start. You have around 7 minutes, and Elsa will give hand gestures of when you're close
All right, don't let me
by
interrupt them.
to
We'll do
your
this.
time ending.
Okay, perfect.
All right, let me make this bigger.
All right, so
good.
hi everyone. We are Trust the Process from Concordia University.
All right, wish them luck.
And today we'll be presenting our Troitsky Bridge Building Competition. So in our team, we have Ann Lee, myself, Ruaid, Isabella, and Kayla, and we're all first-year mechanical and computer engineering students. So before we justify our design choices, we'd like to go over our design itself to give you a better understanding of what our bridge looks like.
Hi, so we decided to design a simple highway bridge, also known as a beam bridge. It is composed of 21 groups of pillars. In each group, there is 5 pillars equally spaced to a distance of 3.125 meters apart. The pillars are 1 meter in diameter, and they're on top of a shallow foundation that is a 2 by 2 meter prism that is 20 meters wide. On top, there is also a pile cap that is chamfered for aerodynamic. It's also a 2 by 2 prism that is 20 meters wide. From the shallow foundation to the pal cap, it is all made out of reinforced concrete. As you can see in the front view of the bridge, the pillar groups are not all the same length. It is because for our foundation, we decided to make the foundation, the shallow foundation, 3 meters deep into the soil, and have the pillar also inside the soil for stability.
So moving on top of the pile cap that we had here, we have 8 pre-stressed concrete girders evenly spaced out, which sit on bearing or round, whatever you like to call them. This just helps with, because when there's traffic moving or when there's wind hitting the bridge, you need some sort of flexibility so that nothing cracks. Above that, we have a 0.3 meter thick slab, which is also made of reinforced concrete. And then on both, whatever you can see with the naked eye, we have on both sides, we have 0.5 wide parapets. And we also have sidewalks, which are 1.5 meters wide. And sandwiched between those two, we have our inclined wearing surface, which is inclined at 1%. This is done so that when it rains, the water could move downwards and go through the gutters, which are placed next to the sidewalks. On this wearing surface, we have 4 lanes, which are 2 by 2 on each direction, measuring 3.6 meters each. We also have a median of 0.4 meters in the center and shoulders of 0.6 meters on the sides for any safety precautions. Sorry. All right, so back to the justification of our design choices.
So our bridge was built to replace the seasonal ferry that connects Turso to Clearance Island. We decided to make the height clearance 12 meters, 0.25, due to boat traffic, so it could accommodate tall boats. And also this river is known to flooding, so it would also accommodate the water level rising. The distance between each group of pillar is 24 meters, which means that multiple boats could pass underneath the bridge at the same time.
So now our environmental concerns. One of the concerns we've had was regarding excavation. Our worry was that we might disturb wildlife and aquatic ecosystems in the surrounding areas. This is possible due to the digging needed to put the foundation underground. Another concern we have, which is actually a positive concern, which are the sidewalks. Because we have sidewalks on our bridge, people are able to walk across it or even take their bicycles, which decreases pollution and carbon emissions. And for financial constraints, because our bridge is mostly made from reinforced concrete and pre-stressed concrete, it's cheaper than other materials you may find on bridges. So that's a positive for our bridge.
So I will be talking about the load analysis, so how much weight and the force the bridge can hold. The bridge will evenly distribute the force no matter where it is applied. As you can see in the image, we assume that the cars on the bridge were evenly spaced. The force will be going down, as you could see on the free body diagram. This is made possible due to its wide design. It carries more load than necessary because there are more columns to support the weight of the deck. The columns each have a dead load of 18.84 kilonewtons, and it also has been calculated that 4,230 kilonewtons is the dead load of the deck. The girders are pre-stressed and make them stronger. There are no cross beams on the girders since the columns are not as spaced out, thus they do not need the extra support.
So if we look at our free body diagram, as Kayla said, most of the supports are pins, so those account for the wind load and braking forces and other frictional forces. So there is a evenly distributed load, and then the columns account to put the bridge in equilibrium. And if we look at our shear diagram, we can see that the shear forces are greatest at these supports. So this is the diagram for between each group of supports. And if we look at our moment diagram, we can see the moment is greatest between the supports. If we look at our stress analysis, we can see that the top part of the bridge is under compression, the bottom is under tension, and then the supports are also under compression. The dotted line is just the neutral axis. And so if we look at our points of failure, the potential points of failure are at the supports because of shear failure, between the supports because of flexural failure, and then at the middle of the bridge and between the supports because of the high moment demonstrated in the diagrams.
We got like a level of service of B because we need like not perfect like free flow, and we had to set like free flow of like 90 kilometers per hour, but because of after our calculations we got 80 kilometers per hour. We had 2 lanes and we had a small 0.6 meter clearance. Thus we got like a level of service of B. Thank you for your time. We hope you enjoyed our presentation. We are Trust the Process from Concordia University.
Okay, great. Judges, I'll take you to the judging room.
Can we ask some questions first?
Oh, yes, yes. Oh, you guys can ask some questions.
You guys said that you are first year, right?
Yeah, we are first year mechanical and computer engineering students. Just trying to leave. Can I stop sharing my screen?
Yeah.
All right.
So you got 21 set of piers, you said, group of reinforced concrete pillars.
Yeah.
So how many in total are you planning on putting in the river?
So it's 21, and then there's 5 at a time. So that would make a total of 105 pillars.
Have you ever seen a bridge that would have that many pillars in the river?
No, we were thinking about putting 3, but because our bridge is a bit wider and it has 2 lanes going on each side, we thought the more support it has, the better it would be.
Yeah. My question wasn't more on the 3 versus 5, but the number of them across the span.
Yeah, it does sound like a lot, yeah.
I don't really have any other question.
Did you calculate the maximum capacity that the bridge can hold at one time? Not the load, but the like traffic wise.
Well, I mean, we calculated that like per hour, like it could take like 976 vehicles, and per day it'll be able to handle 6,511. That's like it's the volume of like cars that it could take per day and per hour.
And do you know what the current like need is? Like how many cars are passing in an hour at a peak time in the area?
I don't think I can answer it. I don't think I would know that necessarily.
Does anyone else know the answer? I'm not sure about it either.
Okay, judges, do you have any more questions?
Okay.
All right, then. I'll take you to the judging room.
All right, then. That should conclude the trust the process right now. We will be moving to Troitsky in about 4 minutes, so let's just move in right now. That was the trust the process. How was it for you guys? Did you guys enjoy that one? I think that one was good, to be fair. Pillars thing was an issue, sure, but I loved it. All right, let's move into this. There you go. Yeah, well, hold on, give me a second. Yes, right now, but I'm currently talking to chat. I'm not showing anything, don't worry. Yeah, I can talk if you want to. Alright, there you go. Okay, right now they're getting introduced to each other and all that. We're waiting for the teams to come in. Hopefully, Dude, this is actually a lot better than I expected it to be. I'm having fun watching this. They should be starting at around 11:30, so that gives them 3 minutes left. All right, how are we doing so far in the chat? Oh wait, Shaving Cream, are you with Troitsky? Are you rooting for them? I like that. Let's play some music right now for the time being. What do we have to play? You know what I'm feeling right now? I'm feeling ABBA. Let me play that. Alright, let me play this. Alright, wait, they're starting. Oh, wait. Let's go.
Or transportation.
I'll go next. My name is Justin Drisdale, and I am also hopefully in my last year. And I'm in space at York University, and I've got an internship with the CSA, so I'm hoping to go into that. But if everything doesn't go well, mechanical engineering is my specialty.
Yes, I'll go. Okay, Lynn, never mind. You're ladies first.
You can go next because you're another Justin.
That's true. That's true.
Yeah, the next Justin in our group.
I'm going next. Oh, okay. So I was going after you. Okay.
We got
I'm
two
Justin, the better Justin of the two. I I'm also in my last year at York University doing a mechanical engineering degree. I'm not gonna do a master's after, but I've been really involved in like manufacturing, so that's probably what I'm gonna go into after I graduate.
Nice.
All right,
okay, I'll go. My name is Lynn Kearney. I am in civil engineering also. I am not in my last year. I wish I was. I have 1 year left. I'm hoping to do structural, and I've been doing construction over the summers to help build up my resume to hopefully get a structural job after. Mike, you want to go?
Yeah, my name is Mike Rukondo, and I'm a second-year civil engineering student at York University. For sure, in the future, I'm looking to go into structure if it happens. But yeah, that's what I like, honestly. Yeah.
Got it, man. Got it.
And one more thing I do, I'm a photographer. That's my hobby. Yeah.
Nice.
Nice to know that.
All right. That's everyone? I think
That's everyone.
That is everyone.
All right. Very interesting. So yeah, whenever you guys are ready, you have 7 minutes to present. You can time yourselves however way you like. You guys are good on that end?
Do we share the screen ourselves?
Yeah, I'm already one step ahead of you, man.
Oh, you're better. Okay.
All right. Well, good luck.
All right. Well, thank you. All right. Well, just to reiterate, my name is Owen Hyatt.
I am Lynn Kearney.
I'm Justin Jen.
Justin Drisdale.
Hello, my name is Mike Rukondo, and me and my team members will represent Team Troitsky from York University. We have been tasked to design a bridge in the town of Turso. This bridge will replace the ferry transportation that is being used in the town of Turso, and it has been experiencing closures due to the weather conditions, which usually happens in Canada. We designed this bridge based on the geographic aspects of the town. This town is located in Quebec, spanning to Ontario through Ottawa River.
Okay, so sorry. It's like how Mike mentioned regarding the early closures. It's become an inconvenience for local residents and commuters to find alternative methods of getting into Ontario. So we are here to design a bridge that will be open all year round to eliminate this problem. This bridge will have to accommodate traffic flow between both cities. So to briefly go into the traffic analysis, considering adjustment factors for access points, lateral clearance, lane width, and number of lanes, we go from a base flow speed of 90 kilometers an hour to 57.22 kilometers an hour. And because the bridge is located on residential areas, the speed limit should not go greater than 50 kilometers an hour. On average, 184 cars will be traveling over this bridge per hour. So this must be considered during the design phase to decide the optimal amount of lanes that will be put on this bridge. And lastly, this bridge must adhere to all codes and standards of the city so that it can be approved by the city and residents who will be affected by this bridge.
Next, we have constraints. For this site location of the bridge, we had to consider the terrain and living standards, which demanded no existing structures to be demolished and or modified in any way. We also had to consider the demands of the community in order to conduct a thorough traffic analysis. More constraints consist of making the bridge high enough to allow boats with an average height between 2 to 2.6 meters to pass under, also taking into account for the 487-meter bridge width and accommodating for the floods, which can add up to an extra meter in water height. From the traffic analysis, we assumed one lane of traffic in each direction, and the bridge should support 4,400 tons of weight.
So the main stakeholders that we will be addressing here today, the first one being the residents of Thurso, Quebec and Rockland, Ontario, which is the nearest city on the other side of the bridge in Ontario. They are the main stakeholders as their bridge will be in their cities and it'll be their main form of transportation across the bridge, across the river. Of course, the city governments of each city, Thurso and Rockland respectively, will have great stake in the bridge, as if something fails, something goes wrong, something goes right. It's all about the city fixing that and taking responsibility. The surrounding environment, such as the birds, beavers, maybe bears, we know that there's a national park on the Thurso side of the bridge, and they have a major stake in this, as we do not want to disrupt anything that's going on in the national park. We want to keep everything open. We don't want to demolish any existing structures. We don't want it to be too loud or anything like that. So the main stakeholders include all of the surrounding environment.
All right, so when it comes to bridge design, we went with two steel tied arch cable bridge, shaped to represent our team name. And the arches are angled at a 10 degrees for innovation. If you look at the front view, you can kind of see they're a bit slanted. Yeah. If you go to the top view, you can see that we have a 2% slope from the crown of the road towards the drains. This is because the river is prone to a lot of flooding, so we had to ensure that our bridge had a lot of drainage. The bridge length is longer than the road connections to prevent the road from flooding as well. And lastly, the sidewalks are 4,500 millimeters or 4.5 meters to allow for a lot of pedestrian use and accessibility. So as you can see in the below, there are concrete pillars on footings, and these footings are actually perpendicular to the flow of water to reduce impact on drag and flow in the direction of the flow as well.
Now let's briefly talk about the load analysis of the bridge. There are two main factors that we must consider on this bridge, which are the dead loads and the live loads. The dead load will include anything that's on that the bridge will hold before the cars travel through them, which will include the bituminous wearing surface, the steel girders, and concrete medians. With these three components considered, the distributed dead load of the bridge will be around 64 kilonewtons per meter. Now, let's talk about the live loading. Traffic loading was based on the Canadian Highway Bridge Design Code and a CL 625 Ontario lane loading. This assumes a distributed load of 9 kilonewtons per meter along the span and a point load of a 625 kilonewtons corresponding to axles of a truck. If we add all those loads together and divide them by 5 supporting pillars, we can find that the reaction forces on each pillar is around 14 kilonewtons per meter with a point load of the 625 kilonewton truck.
There are 4 possible points of failure, which are located at the midpoint between each pillar of the bridge. This is where the moment of force would be the greatest. So when a direct point load is applied to the bridge at one of the midpoints, the bridge will fail from displacement at the midpoint.
There are many environmental hazards we have to consider. The main one that we are considering are to ensure the preservation of the Parc National de Plaisance, or the Plaisance National Park in English, on the Thurso side. We want to ensure that the park remains open, as there are surrounding trails that the the residents like to walk and or bike on, as well as a marshland, which is used to swim, kayak, canoe, as well host many forms of wildlife. Of course, the construction will be done in accordance with local standards and guidelines, which means that we cannot demolish any existing structures, so we have to work around that. And due to a consistent flooding of the surrounding area, extra drainage will be added to ensure that the bridge can remain open the entire year. Thank you very much. We will now be answering questions.
Okay, thank you very much for that presentation. Yeah, we'll now start the questions from the judges, 6 minutes.
So Dr. Erkman, you want to start or you want me to start?
Yeah, I can start. Thank you, Dr. Ali.
Yeah, please.
Very good job. I like your presentation, and especially in your report also, you mentioned your consideration for design, the fact that it's being in the middle of a national park, and you I like the way that you commented on what kind of bridge is suitable, the fact that it can be a modest bridge that doesn't take away from national beauty. So I think this is something that stands out, that you considered this. When it comes to structural system, I have a few questions. So why did you prefer something with a 2 arch rather than 4 arch span? First of all, is there any reason that you had an arch and in the middle of the arch you have another column?
So why we had 2 arches instead of 4?
Yeah, because there are 4 columns, isn't it?
Yeah.
4 piers. Yeah.
Honestly, it was just because we that's the design we chose to represent like our team identity. As for
sorry, I mean, just to understand, you just went for it, or is there?
No, honestly, we just went with that design. There was no structural impact. I also, if we went with 4 arches, I don't think that would have as drastic as an impact as a change compared to 2. I think they're very similar.
Yeah, but structurally speaking, now you may made some conclusions saying that the critical parts are the midspan.
Yeah.
So in that complicated system, can you still claim that critical moments are still at the midspan when you have an arch like this? Because this stress distribution is completely affected by the arch.
Oh, okay. Yeah. So, sorry, just to reiterate, so you're worried about the point of failure being in the middle of the span?
Yeah.
Oh, okay. Well, initially we actually went with 1 pillar in the middle, and then we decided that we would have had a more drastic point of failure because the span would have been way too long, according to the bridge codes. So we reduced it by half by adding in extra pillars in between on each side. And that way we reduced the, yes, we did increase the amounts of points of failure, but I think we reduced the impact or the risk of the point of failure itself.
Yeah, the more the better. I agree with this, but in terms of the analysis, the structural analysis, I think it complicates. I don't think you can, still pick the middle of everything as the most critical when you have arches spanning in an irregular manner. So just something to, I think, keep an eye on. And I guess you have to involve some kind of a tool for that software analysis. Yeah. So it will not be as straightforward, because system is complicated. That's my point.
Yeah, it's okay.
Yeah, and also you point out the failures in displacement. What do you mean by that? Is it a serviceability type of threshold, or why would you emphasize on failures from displacement?
Lynn, I think Lynn can answer that best.
Sorry, my Wi-Fi is being unstable. So the reason why we said they would fail from displacement is because it's a possible chance of displacement. We did, from the traffic analysis, we did find that there was minimal amount of cars going over, and we found that the level of service was actually service A. So there was like minimal traffic disruption, and we also found that since there wasn't as much traffic actually going over the bridge because it was mostly people trying to get back and forth from work, or if they wanted to go and see the sights on the other side from the national park, it was mostly tourists and people who needed to go from work. It wasn't a lot of people. So it's not actually a lot of weight that it is being put on this bridge. So when we think of possible failures, we have to think of, okay, if there was going to be a lot of weight put on, where would these placements be and what would the failures come out of? So when we thought of adding more weight in certain areas, we would see that, okay, yes, this probably wouldn't occur because there's such little weight from the amount of cars that are actually going over. But if we were to look at and like stress it at a certain point, we found that it was displacement. It was a form of it's called, I'm at loss of words for a second. The displacement is the
or serviceability.
it would assume it would shape a U-form shape when it displaced in the sense of displacement is what we're trying to say with that. So displacement would be in a U-form down if there was enough pressure at that point, which we don't really think there would be because there's not enough traffic going through to be heavy enough. But if we were to pinpoint and push down and stress at those certain points, we would find a U displacement of the.
For the sake of time, just to give Dr. Ali to ask his questions, I'll stop here. Thank you.
Oh, thank you, Dr. Ekman. So yes, for the sake of, I will not go on the structural, Dr. Ekman's already covered that. So I'm gonna ask you about the environmental. In your report, you mentioned whatever it is included in your challenging document, what you need to take care in the environmental, but you didn't mention how you're gonna consider that, how you're gonna cover that. What are the environmental factors that you take it when you choose your design?
Okay. Right now, we are all right. So we need to move on right now. Next up is gonna be, honestly, this was my favorite one, Troitsky. Right now we're gonna be on Gods of the Bridge. I really love this one though. I love the, I definitely love the design that they have of the bridge and all that. I think that was my favorite one so far. Moving on to the next one right now.
Reflecting off of it, they might be cowering in fear a little bit from the Minotaur, but it's all for the greater good. And now I'll pass it off to William to continue.
Our bridge consists of on and off ramps of 140 meters in length to allow a rise of 7 meters, resulting in a 5% grade, which is nice and gentle considering cold and icy Ottawa winters. The pillars at the shorelines have a depth of 12 meters, and the center pillar has a depth of 25 meters to go down below the water. We have a width of 29 meters to allow for 2 lanes each way and additional barriers between the roadway and large pedestrian sidewalks. The gods, decided to assume or predict that there could be 18-wheeler tractor trailers fully loading this bridge at any given point. So that is what we went with to do our load analysis. So we came up with 29.5 kilonewtons per meter as a distributed load along our bridge across all 4 lanes. And this would result in about 4,000 kilonewtons in the shoreline pillars and about 7,000 kilonewtons in the central pillar.
So the points of failure are that the cables and connections of the arcs might fail due to an overloading on the deck. Arcs have to have like a great enough radius to be stable, which could affect the strength of the connections. As well, our bridge was designed for a specific loading. Thus, if a greater loading is placed on the deck, there could be a risk of breaking the cables. As well, there could be a failure at the support since there is a heavy load mostly on the midspan of the bridge, which is roughly, as Will just said, 7,000 kilonewtons, as well as roughly 4,000 kilonewtons at the end supports.
Moving on to how this project might impact the surrounding ecology and how we aim to minimize that. Firstly, the elimination of the ferry is by nature a significant improvement. Due to the inefficiency of water-based travel, ferry crossings produce 20 to 100 times the particulate matter and 1,000 times the hydrocarbons on a per person mile basis when compared to personal gas burning vehicles. And these values only consider travel time alone. Factoring in lengthy boarding times and any maintenance and testing of the ferries, this effect inflates further. We acknowledge, though, that the construction can be a messy and contaminant heavy process. So when dealing with anything environmental, solving the problem is 50% mental. It's right there in the name. So we put our heads together and conceived of some innovative solutions. The first being all electric builder bots for assembly of the bridge. We've reached out to Boston Dynamics and are hoping for a collaboration there. To reduce contamination of the water below during construction, we will employ an array of Brita filters to catch any particulate matter flowing downstream. Again, awaiting on word for collaboration there.
Okay, so for traffic analysis, we observed the Quebec traffic maps to determine whether there was a lot of traffic in the area, and it turned out there wasn't. It was all green. Therefore, we could assume a level of service A, which is the greatest criteria you could have, meaning the least amount of traffic. With all the resources and the tables given, we determined a free flow speed of 96.1 kilometers an hour. The location is in proximity of Ottawa, therefore there could always be a potential surge of traffics, large trucks or large gatherings. For community impacts, the bridge gives year-round access, unlike a ferry that can only be used during warmer months. With the sidewalk/bike lanes, it gives for pedestrian crossing, which is important because there is a national park on one of the ends of the bridge. And also the bridge is tall enough to allow for marine traffic to proceed underneath. And people will just generally be happier.
Lastly, activism is on the rise. And unfortunately, this includes activism for imagined or otherwise whiny causes, as we saw recently. For this reason, we saw fit to consider noise pollution and mitigation thereof when designing our bridge. Unfortunately, due to time constraints, we were unable to see this goal through to its fullest potential. The original intention was to integrate baffling structures on the interfacing surfaces to diffuse any excessive sound sourced from the bridge. That being said, concave curved shapes are known to redirect and amplify sound back towards its source. Hence why domes have historically been used for theaters before the advent of microphones and speakers. Similarly, we believe that the archways in our design will serve this purpose twofold. In the event of horns sounding, as an example, the sound will be partially contained from escaping and redirected and amplified back towards any freedom lovers that may be causing a ruckus.
Thank you very much. That is our presentation. We are the gods of the bridge.
Okay, thank you, Gods of the Bridge. So now we will have 7 minutes of questions and answers, and you can stop sharing your screen now. So, judges, the floor is yours.
So I'll start. Gods, if I may address you. So I was curious, what loads did you consider in the design of this bridge?
So we considered the live loads of the tractor trailers. We were still in determining what the dead load would be of the arch and the cable. Sadly, it was a little bit more difficult finding that. Hence why we went with the assumption of the worst case scenario for the live loads.
Okay, so were there any other live loads that you might wish to consider, seeing as you have pillars in your design?
Yes, so the water is another load. We have sent such a large pillar in the center. It is 8 meters in diameter or across to deal with the water, and as well as it's there for wind sway.
Okay. I'm trying to think of something. At one point in your presentation, you mentioned 4 lanes, but in your report, I thought it said 2 lanes. Can you
2 lanes
clarify?
each way.
Okay. So you have 2 lanes in each direction plus your pedestrian.
Correct.
Okay. So why did you choose to do 2 lanes each way?
We chose the 2 lanes each way based off of some of the information we were given, some of the factors based on in the curriculum. So they had factors based off of 2, 3, 4, and 5. And yes, and with a 96-kilometer free flow speed, wanted to allow for 2 lanes.
So as such, we can deal with a lot of throughput of traffic. The reason for this is because we expect a lot of growth in this region. Currently, this would not be necessary. The road right after is 1 lane with a 30 km/h. So realistically, right now, it would not take all this traffic. But we foresee if Ottawa keeps growing, it would grow into this region. This park is very popular. So we are prepared for growth of the region, for the expansion of the nearby roads. And we want the bridge to continue to be useful in future years.
Okay, thank you. That answers my questions.
So I'll go ahead with my questions. Great presentation and great team spirit, guys. Really appreciate all of the gods outfits. So looking at the report and your presentation, you guys did go over potential points of failure, but did you guys sort of could you guys think of any other ones that you guys mentioned with the interest that it is over a river?
Yeah, the center pillar itself could be a point of failure with constant water flow along it. It could eventually erode and decay the pillar, as well as any boats with unsuspecting heights that are unaware of them, i.e. Sailboats who might not know they have a certain height.
Perfect. And now for the actual model itself. In the presentation, this is where you guys showed off the 3D model. I didn't really see any cables or trusses connecting the 2 arches to each other, like the ones that are parallel to each other. Did you guys consider this in your design, or is it supposed to be just independent of each other?
They were, they are independent of each other. They were considered, but due to time constraint, I was unable to get those in.
It was also a design decision due to the sheer height of the Minotaur that is going to be watching over this. We need to make sure that he had access to be able to get into and reach the center of the bridge if there were any problems that needed to be dealt with there.
Okay, and did you guys consider him as a live load?
He would not be climbing on the bridge. He's large enough, he could just wade through the river. We did consider the waves he would be making, but the bridge is tall enough, it shouldn't be a problem.
Okay, nice one, nice one. And for the depth of the actual pillar, what did you guys consider for the depth, and what you guys said that the maximum clearance from the water to the bridge was 7 meters, right?
Correct.
So what's the remaining depth to the riverbed that you guys considered in your design?
In the center, based off of the water depth, it was 11.2 meters or 38 feet. So we went with a 25-meter pillar to allow for an additional 6 to 8 meters below the bottom of the riverbed.
Perfect.
I also just want to clarify, it's slightly more than 7 meters between the bridge and the water, because the water will fluctuate. It's in a flooding region. It's 7 meters from the land, and the land is a bit above the water. So basically it's 7 meters. If the water floods to above the road, then I mean the bridge will be out of use. Hopefully the river doesn't flood that much, and if it does, the entire infrastructure of the region needs to be changed. But as long as the water's below that level, there's at least 7 meters.
Okay,
and
perfect.
we're buddies with Poseidon, so I mean it's like it's not going to get that high.
Fair enough. That was going to be my next question as to what's the the lowest clearance between the water and the bridge. But if it's you guys said it would be 7 meters at the point of at either point of the bridge, right?
Correct.
Okay. Oh, that's good for me. Tilesh?
I had 2 questions. One of them was answered during the presentation, and one of them Anne picked up on it. Other than that, I really liked your presentation. Great work, guys.
Thank you.
Okay, so if there's no more questions, then the judges will be moved to the judging room, and participants, you can stay here.
Wonderful, thank you.
Thank you very much.
All right. This also concludes the Gods of the Bridge. I think this one's the most creative one so far. Let me just try to move us to the multi-force members. This is going to be the upcoming one. Again, I hope you guys are enjoying your stay so far. We got the multi-force members. Hold on. Should be right here. Let's see it loading.
Perfect. In that case,
Perfect. Just in time, eh?
We can begin.
So we're the multi-force members, and we present to you the Panisar-Kwan Bridge. This bridge is a cable-stayed bridge with a harp system. So here are our members. Today, Daniel could not join us because of work. So here's the length of the bridge. Our actual bridge is 480 meters, and we have an additional 2 additional 85.2 meter ramps on the sides. So here's an initial sketch of our design. And here's the deck cross-section that includes the concrete barrier rail, the sidewalk, and the asphalt, as well as the girder that makes up the deck. Here's a top view that shows the layout of the lane, the curb, the concrete barrier rail, the sidewalk, and the urban shoulder. And here's a front elevation view which shows the span of the entire bridge along with the ramps. And finally, the girder details that makes up the deck.
Now for the purpose of the bridge. In short, we're building a bridge that will connect the communities of Clarence and Torceau over the Ottawa River. Now for the justification of our design. To connect these communities, we will use a harp system cable bridge. This type of bridge offers high stiffness, a safe in material usage, a high amount of redundancy, and it serves a quite nice aesthetic purpose. Here are some of the numbers and constraints that we use for the design of our bridge. And in the next slide, really the only thing of note is that our lengthy ramps will be on land, and as our nice existing roads to accommodate them, this will avoid messing with the flow of the river and allow for great accessibility. And finally, this is a simple table that we use to determine the number of stay cables based on the length of the bridge.
So in terms of our material justification, we came up with this diagram illustrating the forces on the bridge. So from what you can see, the cables are going to be in tension while the towers and the deck are going to be in compression. So these forces influence our material choices. So for our tower and box girder, we decided to make them out of pre-stressed concrete because they do very well in compression and have a minimum strength of at least 55 megapascals. So also in terms of financial consideration, they're also very economical, and then they're also very durable. And our stay cables are going to be fabricated from high strength steel. And each strand will actually have a strength of 1,860 megapascals. And we're going to interweave 9 of them together for increased strength. And finally, for the foundation, we chose to use pile caps, which will be made from reinforced concrete, and they'll be able to overcome both moment and shear forces from the tower. They're also suitable environmentally because the surrounding areas are going to be wetland areas, and pile caps are going to be strong enough to withstand the forces around there.
Next, for the load analysis, so we accounted for 2 types of loads, live loads and dead loads. For the live load, we took it from the US Department of Transportation. It's a constant value of 9.34 kilonewtons per meter, and it's distributed uniformly. Then for the dead loads, we accounted for the different components of the bridge, such as the concrete barrier, the asphalt, the concrete post-tension deck. And we did this by finding the volume per meter and multiplying that by the density, which is different depending on the material, as well as the gravitational acceleration. We summed all of these loads together to get a total load of 346.1 kilonewtons per meter. And we use this to inform our potential points of failure. We found that the point of maximum moment occurs midway between each pair of cables. For the shear and bending moment diagrams, we assume that the ramps are pin connected to the main span of the deck, that the columns on either side were pin connected to the deck as well. For the tributary areas, to assign the loads to each cable, half of the deck went to the left tower and half of the deck went to the right tower. As well, you'll find that the elements of our bridge are repeated, such as the right triangles. So we only needed to model one part of the bridge in order to find the points of failure. And as I mentioned before, all loads were evenly distributed. So as you can see here, we have some different FBDs to model the different forces, the downwards distributed load, the upwards tension forces, as well as the reactions. Note that the cables meet the deck at the same angle theta, so that made all of these tension forces the same. And we only took into account the Y components for the purposes of the shear force and bending moment diagrams. You'll find that the maximum shear force occurs where the cable meets the deck, meaning that the maximum bending moment will occur between each pair of cables, as I mentioned before, at a value of 8,600 kilonewton meters.
And now for the environmental impact and sustainability. Here on this map, I noted some points of interest. The red dots indicate a man-made bridge that floods quite often. The green and blue dots are susceptible to groundwater pollution, as there are two parks. One of them is a national park on the north, and the bottom is a fishing spot that is quite popular with the locals. And finally, in a more global sense, we will be using a concrete that is of the style of EcoPact as a way to reduce CO2 emissions.
Now for the traffic analysis. Using the base free flow speed of 90 kilometers per hour, we adjusted the speed based on the lane width, which is 3 meters, the right shoulder lateral clearance, which is 1.2 meters, which is a bike lane as well, and the number of lanes, which is 2, to have a total free flow speed of 70 kilometers per hour. We determined the speed limit on the bridge, which is 50 kilometers per hour, based on the speed limit on the surrounding and connecting roads, which is 30 kilometers per hour and 50 kilometers per hour. Using the Toronto's transportation guidance rules, we, based on a curb shoulder lane, the minimum bridge lane width is 3 meters, so we use that in our lane width. And we determined level of service to be level B because the surrounding populations of the towns are quite small. And we would assume there's not going to be a lot of traffic buildup on the bridge. So that's why we assume level B.
And that's all for our presentation. If you have any questions, we would like to open the floor for them.
Judges, you can ask your questions now.
Great job, guys. What's your background? Are you guys all in civil or? Yes, all of you.
Yeah, we're all in civil. The girls were all in second year civ, and Sasha is a first year civ.
Okay, cool. Just curious. Did you guys consider doing 2 lanes in each direction? And if you did, like, why did you stick with 1 lane?
Basically, we know the traffic in that area is not a lot because it's in like a pretty rural area. It's coming from national parks, so we didn't think we needed 2 lanes. Also, 2 lanes would greatly increase the length or like the width of the bridge, which means greatly increasing the materials used to build the bridge, and it'll make it a lot heavier and it'd be a lot harder to support it. So that's why we stuck with 2 lanes.
Additionally, the road that is already there is only 2 lane in going either direction.
You guys have any other questions?
I'm good. It was a good presentation, guys. Good job.
Okay, thank you. We appreciate that.
We'll be back with some feedback.
All right, this moves us towards the next one. Wait, hang on. Which is supposed to start at 12:15. We have 7 minutes left. Around 7 minutes. 8 minutes left, actually. I'm trying to get confirmation of the next one, which should be the Sunrise Timber. Quick minute. We'll try to move you guys on to the next one, which is going to be the Sunrise Timber. Since we're having a break right now, how are we doing so far? I genuinely really like these ideas. I think my favorite one so far is the Troitsky and the Gods of the Bridge. I think they were really the most creative ones. What do you guys think so far? Hold on, I want to play music while we're doing this. What do you guys think of lo-fi? We have 8 minutes to kill right now until the next scene presents, hopefully. Where is it? There it is, found it. There we go. How's that? Alright, let's join the next breakout room. I'll mute it for the time being. I'll mute everything really, but there you go, let me grab that one. There you go. All right, there it is. Okay, let's mute the breakout rooms. Move to the next one, which is gonna be Sunrise Timber on 1. Nice. I love the layouts. Yo, the host of the competition didn't really agree with that. I did it anyway. I genuinely think it's a really good design. I had too many on the background anyway. It's a bold move, apparently. Do you guys do this? I'm hoping that you do, because there's no way you guys lit it on the default setting. Because I generally think at least I used to change it often. Mine, I used to change it to I used to have mine have like a Mickey Mouse layout on it. I thought that was pretty cool. Now it's a diagonal line. Yeah, sure. You know, we're designing bridges. I'm bridging both corners of my screen. You know what I mean? If it works, it works. Not complaining. All right, so next presentation. Right now they will be taking a break until 12:45. That's going to be the next presentation. Right now we have Sunrise Timber. Next one's going to be Despicable Bridge. I think that's a cool name. Atlas Engineering Creative. Hello Super Billy 123. Can I get poggers in the chat? Okay, sure, man. Well, a long time on that word, isn't it? Honestly, the poggers era over Twitch was the best era. Didn't they like change? I like your accent. Yo, thank you so much, man. I appreciate it. Here you go. Have a puck, champ. It's cute. Thank you. Kick W. Wait, what streamers do you guys watch then? You know what we could do? We could where is it? Have you guys ever tried Word on Stream? Bueller. OTV, of course. TSM, of course. I mean, I think I'm most familiar with OTV because of, you know, live stream fails and all that, right? Because I think they're Bolo. Is it Bolo? Where is he from? I've never heard of him. Hold on, let's search him up. Let's see where he is. Bro, I have so many tabs open. This is a mess. Hang on. USA Rainbow Six Siege. Oh, okay. Plays for TSM. He's the best. He just got a world championship. Stop. That's so cool. For Siege. Oh, let's search him up. I want to see him. He's called... Okay, so it's twitch.tv/Bueller. Is he live right now? Perhaps. Bolo. Bolo. My bad. Bolo. If Bolo... Where is he from, man? What's it? Where is it? Let me see. Where is he from? Let's Google it. You know what? Let's find out. Where is Bolo from? Oh, he's an American. He's from the heavens. Oh, that's cute. If Bolo has 1 million fans, I am one of them. If Bolo has 10 fans, I am one of them. If I have no fans, that means I am no more on earth. If the world is against Bolo, I am against the world. I'll vote in my last breath. Nah, that's passionate, eh? He's the Lord and Savior. I'm gonna take a wild guess and say that you guys play Siege because of him. Or did you guys meet him through Siege? like through watching content on Siege, or do you guys is it the other way around? Oh wait, you don't play Siege, so you just That's passionate, isn't it? Doesn't Siege have like competitive and ranks and all that? Hey, listen, let me give you on that one. I have never played TFT. Yeah, I know, but yeah, I'm saying like, what's you guys' ranks? You know what we could do? Hang on, I have an idea. I could do this. You're Plat 3, is that high or low? What's the average? I'm Platinum 1 on Valorant. That's low? Unlucky. It's okay. It happens to the best of us. Let me see you. Oh, there's a tracker for a rainbow. I never knew that. You know what I could do? Look at this. Hang on. Let me share my screen. Have you ever guys tried this game? Do you guys want to play this? No, it's not Wordle. It's Words on Stream. Okay. Wordle is a different game. Words on Stream is basically everyone can play. You have to figure out the... Well, I think it shows you, innit? Let me see. Okay, well, it just starts. That's very loud. Music off. You don't want that. We have music. Okay, so there's the letters, and you have to basically type words for the letters. So right now, if I do this, you can type it in the chat, by the way. So it should be this, right? There you go. Hey, shaving, stop. You're so it, man. We can't let that. Oh, wait. All right. Hop. Rope. Oh, that was good, shaving.
Okay, it's me.
What does that give us? Did we pass level 1? Yeah, we did. Okay. We'll be fine. Maybe? Oh, that was good, bro. Dude. Last 5 seconds and you win. All right, so now that we finished this, that's going to be level 1, right? And we can basically escalate Mechanical engineering. That's cool. How's the statics going on so far? Term, obviously. Let's go do this. Meteor. Not bad. Oh, you know what else we have? Oh, you stole it. And against Calc. Against Calc too. Someone's a little passionate against the class, isn't it? Meh. Oh, we have this. Oh. I can't send it. It's identical. By the way, I'm unique in the chat, if you guys were wondering. Is Rome... Oh, there's no E. There's no A, sorry. How about that? Nice. Metro. Not bad shaving cream. Look at you. Actually proud. Tor. Oh, we already had it before. Ream, technically, sure. If the website was Arabic, I mean. Tome. Rome. Just put any name that you can. It's okay. We got this. We'll get it at one point, innit? Alright, we did win this level though. Okay, this is where it gets hard. I usually fail at level 7. Or we usually fail at level 7, right? Let's try this one. How we doing right now? Canadian Goose. Oh, it's the... Bro, it's the official Canadian Goose, obviously. How's that? Oh, heck is the word. Yeah, sure. Oh, hockey. See, that's a little ironic, isn't it? Choke. Oh. Maybe? Yes, let's go, boys. Level completed. Okay. You guys are handling this easily, bro. Maybe I shouldn't have underestimated you guys. Eh? You know what? We'll go up until we'll go up till the final level that we can. What else do we have? Got one last word. Whoever gets it, I respect you, dog. I don't have anything to offer, but I'll offer my respect. Shaving cream. Dude, shaving cream is carrying right now. I love it. All right, we're doing not bad. Who's the first one? Shaving cream. He's carrying, man. He's like twice as much. Billy, come on, you got this. That's me. Yeah. Okay, what about this one? Diamond. Noah. Is Noah a word? Damn. What about mid? How do you say iode? Like a you know, negative iode. Moan, sure. Made. Made. I meant, yeah, I meant to spell made, my bad. Oh, a Honda. Let's get it. Is that a word? No, it's not. Is it, oh, there's a fake letter. Oh no, we're not gonna lose, innit? Nah, bro. Not now. Not like this. Oh. Okay, H is the fake letter. It's the one I've been using the whole time. No, chat. Nah. Wait, did it? No, we lost. Nah, man. Level 9. I was unlucky. we could play Wordle if you guys want to. Seemingly you guys are excited about it, innit? Alright, let's play Wordle. No, not that one, right? Unlimited, right? Is that the one? What's the one that streamers use usually? What do you guys say? What Wordle do streamers use to stream? Yeah, sure. There you go. Huh? Tom's Guide. Yeah, sure. Is it that one? Because the normal Wordle doesn't allows you one word per day, innit? Alright, shall we? Alright, let's start with Crane, obviously. Okay. What do we have? So none of them exist except Crane. Farts, no, okay. Okay, Blame. No, there's an A. Bloom. No. Let's try blame. What do you guys think? Bloke. Yeah, I mean, yeah, sure. It's actually not bad. Okay, so we have L and E. Hole. No, but there's no O in it. Solely? While. Ooh. Ooh. Okay. Style. No. Oh, we're so close. Smile. Oh, maybe? No! Chat. Okay, so it's not any of those letters, right? So we need to just look at the keyboard and just figure out what's... Style? No, there's no S. Bro, this is actually a lot harder than I assumed. Is Guile? I don't know. Let's try it. Oh, come on. No, none of those letters? Wait. Nah, we're getting scam chat. Chat, we're getting scammed. Exile. We used E. No. We used E. Oh, E exists though. We don't know though, right? Maybe? Exile? It's a double. Stop. Actually not bad. Yo. Alright, let's do this again. Actually, okay. Let's try to beat it in less than, 6. Shaving Cream be smart facts. Yo, he carried us in 2 games so far. Okay, let's start with what's the most optimal word, chat? Because it used to be crane, right? And then the new video came out. Is it thing? Crane be boring. Adieu. Yeah, I've heard of adieu. My girl also taught me about adieu. Right? Because it has the most like vowels and all that. Except the O, obviously. You try it? Let's try it. Oh my. Okay, there's a D, right? What else? Let's try thing. Let's try like a random word as well that would not match up. There's I. Thunk. No. Wrong? Yeah. Is that a good word? Drown? Oh, drone. There's no E though. It could be drown. No, but the O isn't in the middle. It's not in the middle. O is not in the middle. Also placement. Yeah, exactly. And R isn't there. Crown. No. So, I don't know. What do we have? What's it with me and middle O's? What's that? Okay, so it could be like sewn. Like it should be like OE, you know? Or north. No, node VPN. Okay, so it's Don. Adon. Nod? Nodda? Nodda. Nida. Non-da. Ah, nonda. Okay, let's have another word, right, chat? Right? Let's use all the letters in the that we don't have right now. It's gonna be thing, right? No. Hinge. No. Yeah. See what we did? We just used out all the syllables. Scythe. Puns. Ooh, puns though. Ooh. Oh, I like that. Songs? No, O is not there, that. Oh, my bad either, yeah. Dongs. It's already been 30 minutes. That's crazy. That's actually crazy. Alright, wait. Let's finish this up. Let's finish this up. Quick. Go. Hear me out. Scythe. Not a oh. Game doesn't like it. What if I just unmute the whole thing? Hold on, let's see what happens. Okay, well, I'm muted. Just chilling, you know? Yeah, sure. I think we just admit defeat right now because it's too late in it. As soon as I see the presentation room like just gets inhabited. Inhabited? Is that the word? Habitized. Hey, you need to help me out. You have 2 minutes. Dinos? That's not a word. Not a valid word, isn't it? Alright, they're joining. Come on, last word. Anyone, last word, and we'll go. Last word. Dinos. It's not a word. No, it doesn't tell you what the word is. Alright, we do have to move on. Alright. Let's stop this.
We did not talk about it too. We just guessed that something to wear.
Okay. Yeah, I'll let the judges introduce themselves.
All right, let's go. All right, yeah, have good luck. All right.
So my name is Sabah Ali. I have a PhD. I'm professor. I teach graduate student at Carleton, and I also teach undergraduate at Algonquin Queen College. I have experience in infrastructure and project management for more than 40 years. Thank you.
My name is Emre Akman. I'm an assistant professor at Concordia University Civil Engineering Department. I had my PhD 16 years ago at University of Ottawa, and my field is mostly on computational mechanics, computational modeling for structural application purposes. Thank you very much.
Okay, thank you. For you guys, would you like to say your programs and what year you're in, or will you say that during your presentation?
I guess I could introduce us quickly. So we're all in the same program. We are in civil engineering program at BCIT, British Columbia Institute of Technology, and here in BC in Vancouver. So this is me, Tuan, Brent, Armin, Omar, and Corey. So me, Brent, Armin, and Omar, we're in the same year. We're in 4th year civil engineering, and we're graduating this spring. And Tuan and Corey are in 2nd year, and they're graduating with their diplomas this spring as well. This is our team.
All right, nice to hear it. So you guys have 7 minutes to present. You guys can keep track of the time however you want. Do you want me to do something on my end? Or you guys are good?
Oh, it's fine. I have a timer here.
All right.
I have a question. Do I share the screen or?
Yeah, so you can share your screen and you can start whenever you guys are ready. Good luck.
Perfect. Thank you. You guys can see?
Yes.
Perfect. So yeah, before we start, team, please unmute yourselves. All right. Let's start presentation. How do I start it?
You could go on slideshow and press view show.
View.
Yeah.
Can you guys see my screen? Everything good?
Yeah, but you are showing us the presenter view. You should show us the other view. You share a different screen.
Share different screen.
Vlad, do that again. And then there's that 3 option icon at the bottom. You can change it to the not presenter view.
I cannot see that. Nope.
Like the 3 icons at the bottom.
Custom slideshow.
No, slide from beginning. Click that.
The 3 dots.
The 3 dots right there.
Oh, here. Okay.
And then change it to
hide presenter
other mode. Yeah.
Is that better?
Yes, now it's better.
Perfect. Okay, so 3, 2, 1, we start. Hello, everybody. So we are the Sunrise Timber team from BCIT, and this is our 2022 Troitsky presentation. Oh, there you go. So as for our team, the team is composed of me, Vladimir, Brent, Omar, Armin, and Corey and Tuan. And the representative roles of our team members can be seen on the screen. So as for project overview, our project included the civil 3D model of both the surface and the bridge itself, the AutoCAD model, the load analysis calculations, as well as considered envisioned components. So to talk about the civil 3D surface model, I'll pass it to Corey.
Thank you, Vlad. So I'll be giving a brief overview of the proposed bridge site. The north and south approaches for the bridge will be placed at the existing ferry terminal sites. At the north approach, there's a Plaisance National Park, which borders. So considerations are to be made to minimize and avoid any impact. I took the data provided in the challenge document to show a 3D surface model for the bridge site. The goal was to design a bridge to cross the 500-meter span between Thurso and Clarence Island with varying water depths up to about 10 meters. I attempted to import some land elevation data as well. However, I had problems with the import process, so only the water depths is shown. As you can see, the center alignment for our bridge is shown with a white line crossing. And now I'll pass the presentation on to Omar to give more details of the bridge model.
Thank you, Corey. So after we finalized our bridge geometry, we went and created the 3D model using AutoCAD. So as you can see, the bridge consists of many structural components such as the bridge deck, the pylons, pile caps, piles, as well as the cables. And now I'll pass it to Brent to talk about the AutoCAD drawings.
Thank you, Omar. So as Omar said, we used symmetry to our advantage. It gives a very aesthetic appeal to the bridge itself. The superstructure of the bridge composed of 2 piers and the substructure composed of 2 pile caps with steel piles underneath them. The vertical line there represents the water elevation, and we allowed for 25-meter vertical currents to allow the passage of a typical ferry to go through underneath the bridge along the Ottawa River. We used a diamond configuration for the pylons where the bridge deck actually goes in between of it. And there's a 3-lane configuration as well where the center lane is reserved for a counterflow or emergency lane in cases that there's like road maintenance or there's an accident. We don't have to shut down the whole highway. So to talk more about the design consideration, I'll pass it over to Armin.
Thank you, Brent. So I'll talk about the design considerations. The major design was based on the dimensions of the bridge, as well as a CL625 truck used for live load analysis, and the unit weights of the materials and their volumes for dead load analysis. So for the analysis methods we used an influence line method to determine the live loads on the bridge, and we've shown them here on the table table at the bottom. As well, we performed a dead load analysis based on a uniformly distributed weight of members. So for the traffic analysis, we determined the bridge capacity based on a TOC category, and we found that it would have a capacity of 12 cars per lane in each direction. And then we calculated the demand of the bridge based on the current usage of the route from ferry data and current route data. And we found that 2 cars per lane are actually used, but the demand is much less to allow that the bridge to expand in the future and to the community as it grows to have more, to be able to continue to use the same bridge. So I'll now pass it on to Tuan to talk about, or sorry, to Brent to talk about failure points.
Thank you, Armin. So after we've done our load calculations that we submitted, we analyzed both the superstructure and the substructure, and we figured that the most susceptible to failure is going to be the high tensile cables. Specifically, the cables 1, 20, 21, 40, 41, 60, 61, and 80. So these cables are the furthest, like the longest cables that has the furthest extents from the piers. The reason being is that it has the least amount of vertical contribution, like its vertical force contribution to resist the vertical dead load and live load of the weight is the minimal. That's why it's probably the most susceptible to failure. To talk about the environmental analysis, I'll pass it over to Tuan.
Thank you, Brent. We considered to reduce cost and energy usage using sustainable materials for our concrete and steel bridge, such as recycled aggregate or recycled concrete, as well as recycled steel. Recycled steel would have comparable performance. Also in concrete, cement can be combined with fly ash and slag, which are byproducts from steel production, to also help reduce the environmental impact or requirement for cement. Environmental hazards to be considered were surface runoff and stormwater coming off of the construction site. The surface runoff would contain hazardous materials or chemicals, and so we recommend containing or channeling that water. For example, we could let it collect in an impermeable area, evaporate, and dispose of the sediment. We try to incorporate credits from Envision, and our bridge improves community mobility and standards and infrastructure integration. Now I'll pass it on to Vlad to conclude our presentation.
All right, team. 3, 2, 1. Sunrise timber.
Sunrise timber.
Woo!
Okay, thank you.
This concludes our presentation. We talked about the civil 3D models, the AutoCAD model, the load calculations, as well as our environmental analysis. And I open the floor for any questions. Thank you.
Yes, thank you for, you guys concluded with a bang. It's great. So yeah, we'll have a couple minutes for questions from the judges.
Dr.
So I'll just stop the share.
If you want to go ahead this time, Dr.
Yeah, I can ask a few questions, and I wish I would not take more time. So first of all, I like the report. I like the drawing. I like the aesthetic of the bridge, even though you just violate one of the conditions of the height, but it looks nice. I also like the compatibility between the aesthetics and structure design. But I also very like the environmental explanation. You covered very good points, and I liked it. I have questions about the traffic analysis. So when you said you took the standard CL 625 and you have this, but I did not understand when you calculate the capacity with estimating a 1.5 stop time and resulting in 2 car per lane. Is that 2 car like side by side?
No, that would be 2 cars along on the bridge in each direction. So like in each direction at any time, we estimated that there would be 2 cars. That would be the demand at peak.
The maximum.
Yeah.
So if there is an accident happened at the bridge approach or exit, and then the full deck will be stuck with one side, maybe. Did you consider that?
No, but we have a central lane that's used as an emergency lane, and we would say that would be possibly a place that traffic could overflow in case one of the lanes is blocked by traffic.
Yeah. So in this case, if you exit or you approach, have difficulties from both sides and accidents and traffic jam, then the bridge will be full, right? It will not be 2 cars, no more 2 cars. It will be full all over the span. Cars are waiting for the accident to be cleared before they can move out of the bridge. They will stuck in the bridge. It could be only one side, right? It could be both sides, depend.
Can I just quickly add to Armin? So the 2 cars per lane is just like the demand analysis. But when we did the structural analysis of it, we assumed the worst case scenario where all the 3 lanes are actually filled up with cars. So when we did our structural design for, like, we got about 3,000 kilonewton maximum tension on one of the cables, and there's about 80 of them there. So we assume that the deck is fully loaded with dead load and live load in its own self weight. We just did that calculation to check whether the 3 lanes or 2 lanes each way with an emergency lane in the middle is adequate for the I think the design parameters that was given to us in the challenge document.
Yeah. So to just add on to that, for the actual structural analysis with the live loads, I applied a CL 625. That's the truck that's given by S6, and it's basically the fictitious massive 625 kilonewton truck with the 5 axles, and the influence line method was used to basically move that truck through the critical points of the bridge. And for a simple span, obviously the critical points would be at mid-span for moments and at the supports for reactions, right? So the influence line is a completely determinate, like straight lines. And then I applied those factors between 0 and 1 or 0 and -1 based on where the location of the axle is. And those are all given in the appendices in the report, the methodology.
Okay. Yeah, no, that makes more sense because the CL 625, it would cover all these loads. So I couldn't understand the concept behind the 1.5 second stop on the 2 cars.
Oh, so that was just to see if like under normal conditions of traffic that are experienced currently in the area, if this configuration would allow adequate movement, basically.
Okay, so thank you for the clarifying that. The other point, I think, and then I will give time to Dr. Hartman. You said the tension was the failure on these cables 120 on all these cables because they are the longest cables. That's considered only live load and dead load. What is in this type of structure with the cables and the piers?
Okay, right now we should be moving
what
to
is the worst case scenario
bridge,
that could happen,
which is presentation
as a
room
failure?
2.
Is it only the dead load?
Give me a second.
When we did
hope you guys enjoyed that one.
The load applied to the different pillars holding our bridge, but it was considered during the design of our construction. And we only did the load analysis for one of the 7 sections because we assumed that all the sections would be identical.
For our points of failure, we decided that it would be erosion on our pillars in the water from the chemicals due to pollution from a paper plant above stream in the river, as well as over time the corrosion to the steel inside of the concrete. Failure at the connections is another point between our trusses, as it is modular. This connection will most likely corrode, causing it to basically lose strength.
For sustainability, we use steel as our primary material because it is recyclable and has it's more durable than concrete. So we try to use that for a lot of the design. Our deck is concrete though. We're also the modular construction, like precast concrete, is going to help a lot with the noise reduction factor around like the national park and the surrounding areas. And the erosion of concrete and the different debris is also going to it potentially go into the water, as well as the modular construction also will limit the fuel the spillage that could happen into the water.
For our traffic analysis, we calculate that the traffic flow, or LOS, is a class C, assuming that our FSS is 90 of a base, and then using reductions in the tables provided by Concordia, we got 81 kilometers an hour or 50.3 miles per hour. We assumed that we were going to have one lane in each direction, as the roads going across the water currently are only one lane. If there were two lanes in each direction, that would have caused a bottleneck of people trying to merge, so we left it at one. We also made an assumption using data provided in some links to us that the hourly vehicle rate is 250 vehicles per hour, using the peak time in the summer of 5,600 vehicles per day. So with this, we came to our conclusion of our LOS class C. Using this, we also determined that our road would be a two-way class 2 highway. And thank you for listening to us. Feel free to ask us any questions, and we're here to answer.
Okay, thank you, Despicable Bridge. So you are actually a minute under, so we'll have an extra minute for questions and answers. So we have 8 minutes, and your time starts now. Judges, you have the floor.
Okay, so I'll begin with my questions. Great presentation, and once again, fantastic team spirit with all the costumes. You guys, I can see you guys really went to some lengths to dress up for the occasion. So, as to my questions, for the clearance levels of water, I'm not sure if that was mentioned in the report, but in the presentation, you guys didn't mention what the overall clearance would be from the top of the bridge to the level of the water. I was just wondering if you guys have that offhand at the moment.
It is 8 meters in height clearance.
Perfect. Now, you guys did mention some points of failure, one of which being the erosion on the pillars from the water. Could you guys think of any other potential points of failure along your design?
One potential mode of failure could be in between piers in those sections. If there is too much weight, it could cause the deck to crack. And if it gets too heavy, it could eventually fail.
Perfect. Now, for the pillars, I noticed that on the drawings, they were all the same height. Is that the case, or what do you guys
we tried to have them entrenched in the ground to have at a certain depth, but as the bridge slopes along, it should account for whatever elevation the deck is at that point.
Okay. And what else would you be accounting for, considering that it's a river and the different depths of the pillars?
Well, we tried to have the piers go deep enough that even in the deepest parts of the river, with the water depth levels in the PDF that was handed out, that it would still be deep enough even in that middle piece.
Okay, so you're saying that like even the sections closest to the river sides, they are of the same depth as they would be in the, okay.
Yeah.
Yeah, and I think that's it on my side. Good job, guys.
Thank you.
I have a question for the traffic analysis. Before that, very good presentation. Love the costume too. So traffic analysis, I see that you mentioned 250 passenger cars per hour. I'm assuming that's per lane.
Yes.
Per lane. So then why do you choose LOS Class C when you can choose LOS Class A?
During the calculation, the value I got put it at LOS Class C using a 50-50 with a 100% no passing zone. So it could have been most likely a mistake in my calculation.
Okay, and yeah, that too. And since it's like one lane, don't you want to add a shoulder to that design? Because if it's just one lane going each direction, for example, in winter you have snow accumulation, and then, for example, that's in winter. In summer, you can use it as a safety by lane. Did you process the decision of that, or?
I forgot to consider the shoulder. That was when we were making it wide enough, due to the thought that we put a sidewalk. So it was something that we overlooked.
Okay.
Yeah. Sorry, I just wanted to add one more thing. It doesn't necessarily affect the safety passing lane, but when we were considering the dimensions of the lane widths and the sidewalks as well, some quick research that we did said it needed to be a minimum of 1.6, but we decided to put that up to 2 meters. So it is possible that if we needed to account for some snow storage, that we can put it on the sidewalk as well, and it wouldn't impede too much.
Okay, good answer. The other question is just out of curiosity, why did you choose a truss bridge rather than, did you consider other alternative type of bridges?
As a team, we decided a truss just to do modular kind of design, to be more prefabrication. So it'd be allowed us to have the same parts all through, and it would be easy connections. That was mainly the reason that we went with that, to limit the amount of impact to the community.
Perfect.
That's the main.
Thank you so much. Good presentation. I'll pass it on to Anne.
Love the costumes. I'm a big fan of Despicable Me, so you hit home with me on your costumes. I have a question about the first two members that leave from the ramp up onto the deck of the bridge, like the main deck. What's the slope of those ones? It was hard for me to determine that from your drawings. So you gave us the slope of your of the ramp, the access ramp to the deck being 6%. So, but what's the slope of that section?
Well, the slope of that section should be 6% across. The main goal that we had is that we wanted to make sure we had that clearance. So we started with the middle sections first to have that right elevation, and then we worked down from there just to match up at neutral elevation, or just slope down to 0.
Okay,
so it should be 6% down.
Your slope of that segment is aligns with the slope of the ramp. Your access ramp and your deck have the same slope.
Yeah.
Okay, perfect. So just curious, what other loads did you consider in your drawing? You mentioned water, you mentioned the dead loads, which you did great calculations for. Are there other loads that you also considered?
We were trying to consider, due to the heavy trucks that we did have, but we were trying to find in our textbook a value that would give us an accurate value, but we couldn't find anything in the time. So we forgot to add it in, but we were thinking about in the process of that we would have had a vehicle live load, and then we forgot to add our wind load and snow load to it.
Okay, and being on the Ottawa River, you might want to also consider ice load, because ice is one of the ice uplift is one of the issues that would impact this bridge, because you have so many pillars that is one of the areas that we're considering. But great. I thought it was a great presentation. I really enjoyed your design.
Thank you.
Thank you.
Thank you.
Thanks.
Okay, so if there's no more questions from the judges will be assigned to the judging room, and participants, you can stay here, please.
Which means that I should leave as well. Hold on. Let's next one's gonna be Atlas Engineering, which should be the last one for this event. Let me make sure that it's free. Oh, by the way, while we're doing that, let me show you guys. Actually, the word by shaving cream was actually right. There you go, we got it right, actually. Not bad, eh? Wasn't close at all. Wasn't nervous. We're gonna wait for them to at least start presenting. Let me move this to the side, even. And we'll have it. Hold on. I'll listen to them. Well, you guys are not allowed to, because I'm slick with it. There you go. Oh, they're starting, I guess. So let's just move this back.
Yeah, you guys have 7 minutes, and Timbo will let you guys know in the chat when your time is close by to ending.
All right.
Good luck.
Thank you. So 3, 2, 1, let's go. Hi, we are the Atlas Engineering Atlas Engineering team, and today we're going to present to you our bridge that we did for the Troitsky competition of the 2022 edition. Next, this is the 3D model of our bridge. It is a mix of a bridge with cable and some with pillars. Why we use this is the pillars that support the cables are in the deepest part of the river, and the series of smaller pillars are on the part that are less deep, and so it will be the better model to do not disturb the naval traffic. Next, the bridge is situated in the River Ottawa between Clarence and the small island of Thurso, and the design that we will follow later will be how to take account the length and the some aesthetic reason.
So for the sustainability of the pre-stressed concrete, it can be observed through its innate properties. So the strength, durability, and resilience to extreme weather, and it increases the performance over its whole life cycle. And the precise specification and the high strength capabilities minimize the number of columns and saves material. And it also reduces waste. For the environment, bridges can disrupt the wildlife habitat, the vegetation, and the soil, and the erosive action of flowing water. The high rates of discharge, movement of ice can cause flooding and losses in property. And the cycling pedestrian lane in both directions can encourage the user to opt for environmentally friendly means of transportation. And for the financial constraint, we have to take consideration of the building costs and the maintenance of the concrete, and the combination of cable stayed and bent column system reduces costs and provide more stability during flooding in case the backfill gets washed out, and it's easy to rebuild the ramps. Next page.
So here's a profile or elevation view of our bridge. It's considered a long span bridge with a length exceeding 350 meters as per the Canadian Highway Bridge Design Code. It's made up of a concrete deck with steel girders and a cable stayed middle section with piers on the exterior, longitudinal direction to allow for boat clearance in both the lateral and vertical directions. It should be noted that there are only girders running along the portion of the superstructure with the supporting piers on the exterior, where the cables are no longer extended. So we chose a deep foundation with piles as we need sufficient strength for this very large structure. We also went with piles and a deep foundation as we want to ensure our foundation won't fail under any potential weak soil conditions. So our deck is 300 millimeters deep with an approach section on both sides to allow for entry and exit of traffic flow. Next slide, please. So getting into some more specifics, we chose a 14-meter height above the water level to account for high water fluctuation, as well as mentioned the clearance for boats. The deck width was determined based on traffic analysis, which Ryan will get into shortly. We have 20 cables per tower. The tower height is 50 meters, and the girder size we have 7 steel girders spanning the transverse direction of size W920 by 1,188. So this is one of the largest girders of standard size in the steel handbook with the largest web thickness that I could find to try and avoid potential buckling failure. Next slide.
Here's a section of the top or plan view of the bridge, where you can see that it consists of 4 lanes on each side, and they are each 3.5 meters. The opposite set of lanes are separated by parapets as the speed of traffic is high. On the right of each set of lanes, there is a 1.5 sidewalk or bicycle lanes, and then after that comes a drainage system and a space for the pillars and cables to be connected. The total width of the bridge is about 26 meters. And now Ryan will talk about the detailed traffic analysis.
We conducted a thorough traffic analysis to determine the needs in terms of traffic flow to design the bridge and find some key components such as number of lanes, lane width, and level of service. We aimed for a level of service A, which is the best with free flow speed, and designed for that LOS, but when checking our design using the density, it turned out to be a level of service B, which is still good than what we settled for. We determined that 2 lanes of 3.5 meter width in each direction would be sufficient to maintain acceptable level of traffic conditions. And we determined the free flow speed to be 77.8 km per hour. Furthermore, we included a 0.6 right shoulder for each direction. Using the traffic analysis formulas, we found the hourly volume to be 1,226 vehicles per hour and the annual average daily traffic to be 8,173 vehicles per day, which is fairly high for this location. So we designed our bridge considering a significant amount of traffic, even being conservative, in order to avoid congestion and keep the free flow speed acceptable.
So for the failure point, we determined that the bridge is susceptible to fail at each entries. So this is a figure between two support of the bridge. As per the shear diagram and the moment diagram, we determined that the bridge is supposed to fail at the support due to punching shear or in the middle of the supports because of the highest moment developed. When conducting a load analysis, we determined a uniform on-factor dead load of 585 kilonewton per meter for the superstructure composed of the concrete deck and the steel girder. In conclusion, the Atlas Bridge, which is a combination of a cable stay bridge and a bent column system, is located over the Ottawa River. We think that this bridge is well suited because it provides a reliable transportation route that is aesthetically pleasing and complement well the environment. Thank you very much.
Okay, great. Judges, do you have any questions for them?
They're civil engineering students or what?
Yes.
I think most of us are.
What year?
Makes a civil and building engineering, but yeah.
What year?
Sorry.
3rd year. We have a 1 year too.
Okay.
Maybe one quick question. Why this type of bridge, like cable stayed, and not a suspension bridge? Both can be used for long spans. So what was your thought process for that specific type of bridge?
Well, this
So
bridge is one of the more stable. If the not but stable, but if there's a flood, I like the word in English. Sorry, in French I think it's assage, but I don't think it's the right word. Anyway, when there's a flood, it will be easier and less and cheaper to repair it than a other side because the support are more on the side, and also because it will be easier and cheaper to do this kind of bridge than a suspended bridge with a longer and more complicated design.
yeah, we kind of went with a hybrid.
Sorry?
We went with kind of like a hybrid bridge, so it's not cable stayed the whole way through. It's just cable stayed in the center, which is because we need a lot of support in the center, as well as the water is really deep. So we figured we would do kind of a mix between like a typical highway bridge and then cable stayed in the center, as opposed to like a suspended bridge from beginning to end. And we liked the way it looked too. So
We also took inspiration from the bridge on the 25th highway, which is similar in some sense of ours. And because the distance was pretty close, the 25th bridge is like 500 meters, if I remember correctly, and ours was 530. So that's why we use an hybrid. It was inspired by this one.
yeah, there's a similar design and similar constraints. So we took inspiration and drew inspiration from that location and that already existing bridge.
How'd you choose the 14-meter clearance height?
We just look on the maps to find the closest bridge on the Ottawa River, which was if I remember correctly, the Alexandra Bridge not near in Ottawa. And when I look up on the internet, I found a report that was for the restoration and or replacement of the bridge. And on the report, there were a plan from one of the design choices, and the height between the water and the bridge was 14 meters. That's why we choose this height.
Okay.
I didn't see really any load analysis in your report. Was it like a manque de temps or did I miss it?
Yeah, we only determined quickly the dead load, but yeah, because of lack of time, we didn't go in depth with like live load analysis. We're really rushing at the end. We mostly focused a lot on the like design of the actual bridge on the 3D and AutoCAD. So we didn't have that much time left for the entire load analysis.
Judges, are you done with your questions?
Yeah.
Okay, then I'll take you to the judging.
Okay, well, this does include the Troitsky event. I'm really glad that everything went smoothly. Well, to the most part. This should conclude. So, me leaving the room should be completely fine. So, let me put you guys on this. But thank you guys so much for coming in. We do appreciate every single one viewer. We do appreciate the chatters. We hope that you enjoyed this event, and we hope you like the contestants. And this should be it. All right. Goodbye.